Jason. Welcome everyone. And what I'm going to talk about today is I'm going to give you a little bit of overview of self-time logic, asynchronous design, and I think one project to talk about in a little more detail. I won't talk about most things in detail because we have basically an hour, and then I'll talk about some of the recent progress we made in design automation and tools for developing these sorts of circuits. So, I mean, before I start, I'm going to just make a sort of a philosophical remark about why I design asynchronous circuits. Okay, I mean, you can. Well, first of all, there's a very nice line that I like from a chess playwright who's also their president, who said that work for something because it's good, not because it has a chance to succeed, not just because it has a chance to succeed. And that is, frankly, what I think of as the benefit of being an academic. I can work on crazy stuff. It might be totally stupid, but it's okay. My students will still get jobs. I don't have to worry about that, right? So that's why I work on asynchronous design, because very early on, I was a student at Caltech, and the first class I ever took on chip design was on asynchronous design. Okay, not too many people can say that, because not too many schools even offer a class like that. And what I realized very quickly was, for any synchronous design, I can do an asynchronous design that is at least as good. And so it just seemed natural, like, why bother doing synchronous logic, for me at least, especially since I'm interested in research and an academic, when I know that whatever thing I would do synchronously, I could do a better version, right? The worst thing you can do is write a paper where you can do a better job, right? Even before you started the work. So like, why would you ever do that? So that's why I work on asynchronous design. What is asynchronous design? This is my sort of very simple way to think about this. If I group computation into sort of 4 buckets based on whether your computation is discrete in either the time domain or the value domain, there are 4 quadrants here. 3 of these 4 quadrants are completely non-controversial. And I work on the one that is controversial. Okay, so discrete time, discrete value, that's digital synchronous logic. Discrete time continuous value is things like switch capacitor analog circuits. Continuous time continuous value, like that's like an amplifier, right? And then continuous time discrete value is digital asynchronous logic, and that's what I'm going to talk about. And there are different names that have been given to this field over the years. You'll see terms like data-driven computing, self-time computing, asynchronous, clockless logic, all sorts of different names. Okay, but they're all roughly synonyms. People will argue that this one of these includes a circuit family and another one that doesn't. But in my mind, they're roughly the same. Okay, so I thought I would start with a little bit of history.
Okay, Rajit, when one thing,
yes.
You go back.
Yeah.
And if you look at where do spikes fall in?
Yeah, I mean, the fun part is, usually when I'm talking to a neuromorphic audience, I usually don't have to argue with them for 15 minutes explaining why I do what I do. It's kind of fun.
But someone will say that spikes are also analog.
Yes. Yeah, exactly. It's continuous time, at least. That most people won't disagree with that. Actually, you'll find people who even disagree. Let's not go. But having talked to enough neuroscientists in my life, I know that all opinions are on the table. I'll just leave it at that.
So whatever discussion here is relevant, and that's why we have Rajit here, is relevant because it could provide some abstraction for neural computation, which is spike-based. And that's really the bottom line.
Okay, so this is a very biased perspective. I'll own up to it, since it's my personal perspective. I haven't included everybody. I haven't, maybe there are things I put here that I shouldn't include. But I thought it's actually interesting to have a slightly interesting.
Is the mouse on the computer?
Oh, I see. Got it. Thank you.
Nothing.
Bit of a historical perspective. So I'm starting from like the mid 1940s. So this is roughly 1946. This is the very famous summary of the lectures held at Princeton, normally attributed to John von Neumann, called the Preliminary Discussion of an Electronic Computing Instrument, in 1946. And in that, he argues that, of course, we should do everything asynchronously. It's going to be more efficient. Okay, and the example he uses is binary addition. why it doesn't make sense to do anything else. So roughly in this era, if you looked at the fastest computers in the world, they were all asynchronous. Okay. In fact, there's a really funny technical report that literally spends one sentence discussing the possibility of synchronous logic and dismisses it. Right. This was a technical report at the University of Manchester. They were designing the MU5. This was a successor to the Atlas machine. You may not have heard of any of these machines. Atlas was the first machine with virtual memory. They invented the notion of virtual memory for example. Okay, these are very foundational machines. And they just say, like, why bother? It's going to be, there's no use for adding a clock. It's just going to slow things down. Right? That's literally what they said. There's a very well-known project by Wes Clark, very famous researcher. He did the TX2 machines. He recently passed away. But he had this very nice project called macromodular systems. And the idea was you wanted to build a computer with a plug board. So it's a bit sort of like Legos. And each component had some function. And because you didn't exactly know how things were going to be plugged, they wanted everything to work correctly independent of the physical properties of the computation. How fast it ran, all this kind of. And so, of course, they developed a lot of interesting theory on asynchronous logic. This Molnar is the same as this Molnar, where they discovered, but they didn't discover. They finally got the rest of the world to acknowledge that metastability is a thing, and that's a problem. Actually, what had to happen was the Bell Labs telephone network crashed in the United States. And then they realized, actually, this isn't fiction. But roughly around here, they ran into trouble. I can get into that, but I don't have, I'm happy to chat about that offline if you're interested. The nice thing about working in a field like computer science, at least so far, is there are people still alive who know the history because they lived it, right? So it's kind of interesting. There's the Huffman flow table synthesis method that was developed roughly here. This is the same Huffman as Huffman codes. Yeah. Okay, did a lot of different things. And what's funny for me, at least, is this is roughly what textbooks view as the state of the art in asynchronous design. If you read a textbook published in the last year, this is what they will talk about. If they even mention asynchronous design, this is what they describe. Okay. And by the way, they tell you how horrible it is, and I agree. Okay. It doesn't scale. So roughly around here, they ran into trouble and they switched to synchronous logic. And the big problem they ran into was they couldn't figure out a way to design circuits where signals didn't have glitches, but an efficient way. Okay. You can always make a really bad circuit that does that, but they couldn't solve that problem. Roughly here, this is chapter 7 in Mead and Conway. It's called System Timing, written by Chuck Seitz. That's the first VLSI book, right? And Chuck wrote this chapter talking about why asynchronous design is important, right? And a lot of people got excited about this and started looking at this again more seriously right around it, okay? Especially at Caltech. And then roughly from 1980 to 1990 is the era where some of the core principles of asynchronous design were like, people finally figured all this stuff out. How do you do hazard-free logic synthesis, right? That was a big deal. How do you describe the computation in a systematic way? There's some famous papers here. Martin was my thesis advisor, was at Caltech. They worked out this compilation method. There's chase theory by Jan van de Sepschut. And then there's a very famous Turing Award lecture by Ivan Sutherland on micropythons, right? Talking about, look, it's so simple. You can easily build these things. Here's this one new gate, and you can build anything you want. Anyway, so again, a lot of people got excited, but even then people were like, well, we don't know how to do this. So this, I think, was a big milestone. In 1989, it was the first asynchronous microprocessor ever. That was done by my advisor's group at Caltech in 1989. He showed me the reviews of all the rejected versions of the manuscript. It's kind of entertaining. Reviews roughly said, I'm an expert, I don't know how to do this, so it can't be done. That's my summary of all the reviews. But they eventually got published, okay? And then there was a lot, then people started, hey, I can actually build real chips with this. And what's interesting is, this was a project that was done by about, 6 grad students in 6 months. But the very early era, 2-micron process technology. And they actually outperformed the commercial processors.
That was a chip that was run from Potato?
Yes. Okay.
Sorry.
Okay, to fill in Andreas's add some color to his comment. You can basically build an electrochemical cell by sticking the appropriate metal electrodes into a potato, and that generates what is it? It was 0.7 volts, and that was enough to run the process. That's fine. My good friend of mine did that for fun. Then there actually was a lot of progress in the early 90s, like the mid 90s, where lots of new designs were developed. This is the fastest processor ever built. Okay, this includes every commercial processor in that process technology. Even to this date, this is roughly as fast as you can make a CPU go. Philips Research had a bunch of projects.
But before that, didn't the Silicon Graphics have the division circuit being self-timed?
Oh, not AMD.
AMD,
Yes.
yeah.
Oh, well, okay. What I didn't put in is all the industrial failures that
Oh, I
happened.
see. Oh, I see.
So,
But there was some successes.
I would say that.
Okay.
There were some projects. Let's just see. In fact, I remember when I started as a faculty member, the head of IBM research was visiting. I was at Cornell at the time, and I said, we are working on asynchronous design, and he was like, yeah, we had an 8-year research project, and we couldn't figure out how to make it work. And then I put the picture of my chip on my first slide, like, yeah, here's this one works. And he was wondering how we did it. So I was like, well, then you can ask this person at IBM research. He'll tell you how to do it. But they didn't listen to him. Anyway, then roughly in this era, there was a lot of progress made on lots of different domains. And I put in a bunch of projects here. Probably a very well-known one is a 10 gigabit Ethernet switch chip done by Fulcrum Microsystems. Fulcrum was a spin-out out of the MIPS project, which I also worked on. My friend started this project. By the way, those are the designers who do low-E. Okay, Intel acquired this company. This became the switch division, and that's the same group of people that designs low-E, low-E2, etc. Okay, just some history. Okay, so in the neuromorphic world, I've highlighted some things in green, where they initially at least. So the fun thing is, AER at Carver's lab at Caltech and all the sensory systems that they developed, of course, they said digital stuff has to be asynchronous. Right? This was just an obvious thing. They had local expertise. I emailed various students in his group, like, oh, if you're fixing some bugs in their asynchronous design, I was a student there, just, nothing. Didn't think there was anything special about it. And then after that, something like NeuroGrid done by Kwabena's group at Stanford is also asynchronous. I think the initial higher like GERT's also asynchronous. I didn't realize this, but facets actually is also asynchronous. That's interesting.
Parts of it.
Parts of it, yeah. Yeah, exactly. The communication infrastructure.
Yeah.
I was surprised. We have the first version of Spinnaker. The communication network's also asynchronous. I worked on the True North chip with IBM, which therefore is also asynchronous since I worked on it. low-E Braindrop, these are all asynchronous designs, and so is low-E too. Okay, so lots of very interesting demonstrations were done, but the problem is a lot of these chips were hand designs, and that doesn't scale. Okay, so I'll explain what we've done to address this shortcoming and why it's actually so complicated, and what's difficult about it. But I'll get to that first. Okay. So just to give you a sense of how asynchronous design differs from synchronous logic, I just want to give you sort of an overview of how things might compute asynchronous. Right? Synchronous logic, there's a very well-defined mindset, which is based on state machines. Right? State machines, let's say, globally synchronized, no problem. How does this work in the asynchronous domain? Well, in the asynchronous domain, we think of a chip as a parallel program. Okay? Everything you put in silicon, you can't make it run. You can't stop. I mean, you put it there, you turn it on, it's running. Right? So everything is running in parallel. In fact, the thing that got me first interested in asynchronous design is I thought it was a very interesting cost model, because it turns out that doing things sequentially is costly, and doing things in parallel is cheap, which is the exact opposite of software. Right? I thought that was very interesting. So the chips are parallel programs, the components are processes, the communications via message passing channels, and the way you synchronize actions or order events in this paradigm is by message passing. If I send you a message, then you can't receive it until I send it. And that means that whatever actions follow your receive happen after the ones before my send. Right? So now you know that these two parts of your computation are ordered. That's how you synchronize.
Rajit, when you say components, you mean the computation?
Hardware components, yeah.
Where you do the computation.
Where you do the calculations, yes.
Yeah, calculation, yes.
Yeah. But I mean, sending a message is also a calculation, but in my book, that's not good.
Okay.
Yeah. Right. And at the wire level, there are two sort of very common ways to do this. How you translate this communication message passing into wires. This protocol here is a dual rail protocol. This is a delay insensitive protocol, where I use the word delay insensitive in the same sense as coding theory. What happens here is I have two wires. They're initially both, everything is zero initially. If I want to send a zero, here I send a one first. If I want to send a one first, I raise the one wire, I get an acknowledgement, and then I lower it, and then I reset. Right? So they're ordering, events are ordered, the two ends have to check the signal transitions, and because you do this handshaking, you're guaranteed that you first do synchronization. And in this case, I can unambiguously know, no matter how much delay you put on any of these wires, when I've transmitted a value, I know when to receive the value, I know what the data is. There's no ambiguity. Okay, that's a delay insensitive interface. This is very nice because we build chips that work from 40 Kelvin to 400 Kelvin. We don't have to do anything. We just make sure we use this protocol and everything works. That's part of the reason the first asynchronous microbrowser ran off a potato.
Potato, yeah.
Because the voltage doesn't matter. As long as things roughly behave like a switch, it's going to work. Okay. That was in 2 micron. Actually, the one that ran it, that was in 1.2 micron.
1.2, yeah.
So way below sub threshold. Anyway. This is a bundled data protocol. So the idea here is you have a request and an acknowledge for synchronization. But what I do is I send data along with the request. And this requires a timing constraint. The request in this example, the data must be set and stable before the request goes high. If you assume that, then when the request arrives, you can sample these data wires and you know that you've got the right value. But this is a timing requirement. Okay, so here I can put delays and break the protocol. But this protocol is much more wire efficient, right? I use 2 wires per bit. Here I use 1 wire per bit plus a request, right? So you have a trade-off between how many resources you want to spend and what robustness you get. Okay, so that's roughly the basic idea. Any questions, by the way? Makes sense? Yeah.
In a way, so maybe the first one is less area efficient.
Yes, this is less area efficient.
Not any less energy efficient.
Not any less. Well, depends on your activity factor. But you're
only driving one line, right?
Yeah, you're only driving one line, but here you might not change it at all, right? If you're sending the same value from
So you do coding.
So you might serendipitously gain energy. Okay, in this scheme. There are other coding schemes, by the way.
You can do 1.4, 1.4.
You can do, yes, exactly. But the most efficient coding scheme you can use that's delay intensive turns out to have a penalty of log n extra wires. So with n plus roughly log n wires, you can do a delay insensitive code. Yes.
I was just going to ask on the last slide, it seems like a lot of the more recent projects, like the last 20 years or so, have had an asynchronous version and then they switched to a synchronous version.
Correct.
Why?
Why? Oh, because there are no tools.
So
how are they going to scale? How are they going to iterate? It's very hard for people to design things. And guess what? If you can't pick up a book and learn how to do this because the books say we don't know how to do it.
So most of these projects were like kind of handcrafted.
Asynchronous tools are expensive, especially at Hopkins. $55,000 a year.
Chips are getting
They're unionized.
Right?
I see. That's that timing analysis at scale. It's kind of coming in.
I will explain like the decent stuff that we've been doing. Yes.
Yeah, I was just wondering, like on the next slide, there is an even more asynchronous version if you think about what a neuron does, because you don't have the acknowledgement, right? So
That's right. Oh,
looking at that.
we've got that chips that are built like this as well. You can actually erase this. Don't worry. Plenty of yes.
Okay.
You can do that as well. Yeah.
But to add to Mike's point, maybe it's not just the EDA tools that is a big factor, but couldn't one argue, I'm not going to argue it, but couldn't one argue that if you just have really good clock gating?
Yes. We'll definitely argue that. So, so actually, the counter example for that is my student is submitting a paper right now that shows that if you give me a clock-gated asynchronous design, I can give you a clock-gated synchronous implementation. I can give you an asynchronous design that's just as efficient on energy, but is faster.
But it's faster.
Yeah.
So what you're saying is that this message passing protocol is more efficient than taking a mux and gauging that you don't need particular clocks to run.
Yes, and the reason it's more efficient has nothing to do with that. It has to do with the controller that you need to generate the input to the mux that everybody ignores until you actually count everything, right? So yeah, that's where you lose. Yeah, exactly. So my sort of cartoon view of how computation proceeds in an asynchronous design is you have some function of inputs and outputs, right? This could view this as combinational logic if you want, right? So far nothing has changed. Could be synchronous logic, could be asynchronous logic, right? Even in combinational logic, when the inputs change after some delay, the outputs are produced, right? So there's no difference here. In fact, purely combinational logic cloud is, if you look at the commercial terminology, is viewed as an asynchronous circuit, right? The problem is that's all they view as an asynchronous. So there are many other things that fall into this category, right? So I need something to know to make this asynchronous and not use a timing reference, a global timing reference to say when the result is ready. I need some way to encode that the result's available, right? So I could have a separate wire. It could be implicitly encoded in the outputs. There are different approaches to it, right? So that's one thing. So now I can change the inputs and somehow tell you the results ready. Okay, so far so good? Great. But that's only one thing. By the way, there are lots of interesting papers, I'll say, but if you look at them very carefully, you can only use the circuit once. That's not very helpful because they don't count everything that you need to do to use it again. And when you count that, it's a terrible idea. Anyway, so now you know that the result's ready. So now you need to let whoever is receiving the value has to inform the transmitter somehow that, hey, I have the answer now, feel free to change the inputs again. So no matter how you do this asynchronous implementation, these arrows are logical in this picture, right? This has to be encoded in some way in the signals from the system. That's basically how it works. And as soon as you do that, now I can do this. Clear? Does that make sense?
Just the acknowledgement part, like you could also generate a pulse that is long enough that you could sample it on the receiving.
That's right. This could be implicit. This could be implicit by timing. For example. Yeah. This is a logical representation, not a physical representation. Yeah, it can be implicit by time. Actually, for my startup company, we even have a patent on this. We call it one-phase logic. We can show how you do it.
So, Rajit, let me just also, I know we're taking time, but I want to bring it back also a little bit to the neuromorphic and neural. Yes. Is there any thoughts how this could relate to how neural computation is done? But it has to be asynchronous. There's no clock.
Okay.
Things have to.
Yeah. So there are some interesting. So I would say that.
But we can leave it later. I mean,
I think there is. I actually will. I think the ties are quite deep at the theoretical level.
Yes.
And I'm going to talk about that. I'll explain one of the recent theoretical results that actually is the basis for why we could even write this software tool for. But that paper got published last 2023. I started writing the code in 2018. I knew it was true. I didn't have a proof, but now I have a proof. Okay, so fortunately I wasn't wrong. But anyway. So just to give you a flavor, you can actually design anything you want in this approach, basically, right? Anything you like. Here are CPUs we've built. These are full processors, and something I should tell you about when we do research in my group is I actually want to make sure that the chips that we build can be used. So for example, this is a MIP processor, so we booted a kernel on this, no problem. This was a low-power asynchronous processor for sensor networks. And we had a special instruction set architecture, so we wrote a compiler for it to make sure we can actually use it. Right, so these are some of the chips that we did. These are neuromorphic chips that we worked on that I participated in. This is the Golden Gate chip and True North with IBM, and then this is the Braindrop chip with Cardena's lab at Stanford. These are FPGAs that we built. This one is interesting. It's radiation immune. So that's kind of cool. And then we worked a bunch of signal processing hardware. This is actually, I'm very proud of this project. It's actually really cool. This is with Yannis Siviris's group. This is the last project his group did before Yannis decided to retire, unofficially at least. It's a continuous time IIR filter. Anyway, there's lots I can tell you. We built actually weird things like a GPS baseband. For those of you who know how GPS works, GPS is all about time, right? And we did an asynchronous one. And we cut the power by literally an order of magnitude. This is an interesting paper we wrote because I was at Cornell at the time, and the IP office got calls from some handset vendors. And so then they decided to file a patent application.
Are the FPGAs programmed just using ACT or? With
Oh, no, this, we actually have flows to map to this from Verilog.
Yeah, see.
Yeah. Doesn't matter, right? Yeah. It's easy. You get more efficiency if you program it with something like ACT. ACT didn't exist when we did this chip. Okay. Oh yeah, by the way, this full custom hand layout, full custom hand layout, full custom hand layout, full custom hand layout.
I thought you said no problem. I thought you described those chips. They were all designed no problem. But then
I don't do that as a problem, actually. Not for a research project.
Student's problem.
Not my problem.
where did you from that?
No, I mean, we know how to design it, right? Just takes time.
Like, we're trying to automate Verilog.
Yes, well, let's not go there. Yes, this was also full. This was cut. So actually, in some of these, so I should just to be clear, when we did this chip, the commercial chips were also full custom handling. Believe it or not.
Yeah, at that time, yes.
Yeah, they were.
Because this is really,
They used to actually hire art majors to do this. I don't know if you know this. You know why? Because they understand geometry better, and you pay them less. I'm not joking. I mean, it's literally what was the case, right? Anyway.
So how does it compare in terms of area? If you
So area. So I can tell you that your memories are the same, which is like 90% of your die area. So even if I double it, it doesn't matter. But it depends. So the area depends on what circuit style you want to use. If you want fully robust, then there's a penalty. That penalty is not for the memories, but for everything else. The penalty is roughly a factor of, depending on how you do it, 1.2 to 2.2x.
but memory also, you need it 7, 8, 9 transistors.
No.
Or you can do it.
A normal SRAM has a dual rail readout.
Okay.
Okay, it's delay insensitive readout from an SRAM.
Oh, I see.
I do have to make one timing assumption on right if I want to use a 67.
Yeah.
But you know,
Yeah,
to
that's why
violate that
people,
timing assumption,
that's why people use 7 or whatever.
if you want to really have it be robust,
9,
it's even more. It'll be 12
really?
because it's the same bit as a register.
Oh, I see.
Yeah. It'll be the same bit.
Oh,
of
I
bit.
see. You get it.
It'll be a register bit. If you want a write acknowledgement from each bit.
Oh, I see.
this area penalty, it comes from the additional.
Yes,
Right,
exactly.
right.
Yeah, exactly. The encoding,
Mhm.
the delay insensitive encoding, and therefore every wire has a gate behind it, right? So you can do that. Turns out the circuit level story is more complicated. That's why there's a range. Okay. There's actually been chips we did which was lower area, but that's because we had a different algorithm that we implemented that gave us better performance. That was a terrible idea in the synchronous domain.
Is it really the wires, or isn't there also like a lot of handshaking logic?
Yeah. So,
Right.
but every wire has a gate behind it, right? So that's the handshaking logic. So it's both, right? If you didn't have the wire, you wouldn't have the handshaking logic. So, yeah.
No, so in a synchronous design, most of the area is occupied by the clock tree or all.
Oh yeah, the stuff that no one counts in that paper. Yeah. Exactly. Only I mean, that's why ISSCC papers are kind of nice because they measure it all. But of course, we know how they play that game as well, but you can figure it out from the paper as well. But anyway. Okay, right. So just a quick sampling. So of all the projects we've done in this space, I'll spend about 5 minutes talking about a particular project since it's actually relevant to some of the topics that we have been presented already, which is a combinatorial optimization using Ising machines. This is a joint project we're working on with Professor Rajit Manohar at Berkeley. So for those of you who don't know what the Ising problem is, so it's quite straightforward. There's a graph. Every edge in the graph has a weight. S1 through Sn, these are the vertices in the graph, and the Jij's correspond to the edges. And there is a summation that looks like this. The cost function, the Hamiltonian, if you're a physicist, right? This comes from the Ising spin glass model, which Gert alluded to yesterday, right? Is you take the product of Si and Sk, and you weight it, you might put the minus half, depending on whether you read the CS version or the physics version, the sign flips, doesn't really matter. Okay. Each spin variable is +1 or -1, and the weights are symmetric. Okay, that's the setup. And you want to find the assignment of SI SJs, that's just combinatorial because they're integer valued, only two values, binary, right? That minimizes this function. And there's an alternative formulation which was mentioned earlier called Cubo. The only difference in Cubo is that the weights are, the sign is either 0 or 1 instead of +1 and -1. I like the +1 -1 formulation for symmetry reasons, but it doesn't really matter because you can just convert between the two by this variable exchange. Very straightforward. And just to give you some intuition, if this weight is positive, you want SI and SJ to agree, right? Because that makes the sum more negative, right? So this problem is trivial if all the weights are positive. This is just pick all +1s or all -1s and you're done. That's the solution. And then it starts getting interesting when that's no longer the case. So you can actually tune the complexity of the problem as well based on the signs and things of that nature. This is actually this is a very old problem, right? From 1920s, if I remember correctly, roughly that era. There's actually a very nice paper by Hopfield, in PNAS in 1982, where he talks about essentially solving this with the Hopfield network. And very straightforward. It's not very complicated. People make a big deal out of this, but it's actually not that complicated. In there, you have neurons, each with an output, right? That replaces my sign. 0 is a not firing, and 1 is maximum firing, 0 and 1. The time evolution rule is quite straightforward. So those JIJs that were there, those are coupling weights. Those are the weights. Everything is connected to everything else with these coupling weights, right? And the time evolution rule is basically the firing rule, right? You have a threshold detector, and if it's positive, you set the output to 1 and you set it to 0. So this is a standard neuron, one of the standard neurons. Okay, make sense? And you can sort of see what happens to this particular quantity, which is basically exactly the same as my Ising Hamiltonian, right? If this sum is positive, this VI gets set to 1. So setting it to 1 is going to make this sum more negative, right? Very simple. And you need the symmetry. You can work out. I mean, I've only shown you one piece, but it's symmetric. So it turns out that that's actually correct. If it's not symmetric, this is no longer true. But that's it, right? So this time evolution is at least doing a local gradient descent, if you want to think of it that way, right? And then, of course, you have to throw in stochasticity and things like that to get a distribution of solutions and so on, right? So this is roughly how these things work. So this is one way you could go about trying to solve the Ising problem, where we should give you a distribution of solutions.
Yeah, and 40 years later, the guy got the Nobel Prize for this.
I don't know what he got it for, but
Yeah, but yeah, this is really computed. Yeah,
Yeah.
and that's really
a lot of things in his life. So.
no, but this is really what they said.
Okay. So we decided to, so my collaborator is Professor Rajit Manohar at UC Berkeley, and he has a long-standing line of work in his research group on analyzing nonlinear coupled differential equations and oscillators in particular. And so the approach we were looking at was to use what he calls oscillator-based Ising machines. Okay. So how does this work? This is a very nice picture from one of his papers, so I just stole it. So if you have an oscillator that's just running around and you're looking at the phase, it's 0 degrees, depending on, whatever. You can see the phase evolution over time is going to, it's just how the oscillator is free running. Now, if I have a bunch of these oscillators, I can injection lock them, okay, at some frequency. So there's some natural frequency for each oscillator. These are analog oscillators, effectively. So and you could use a ring inverter, but it's still an analog oscillator, at least in this model. And they're free running oscillators, and so they have some locking range. And so you can pick a fixed frequency that hopefully, this is you have to be careful when you engineer this when you have enough oscillators that their locking range in fact overlaps. That's not actually a trivial thing, it turns out. So you pick that frequency and it's going to just lock, right? If everything is done correctly, you can injection lock all the oscillators. That's not very exciting, right? it's not very exciting that all the oscillators are just doing the same thing. But now there is another interesting thing you can do, which is instead of running this at F1, you run it at 2F1. And then what you get is you get subharmonic injection locking. So you either lock in one of two different phases. Okay? Again, if there's some math you have to worry about to make sure everything lines up correctly, but you can make this work. And now here's my +1, -1 representation, is which phase did I lock? Okay. Yes.
So if what's injection locking?
Injection locking is if you have a free running oscillator and I appropriately couple it with an external signal that is also oscillating, then when all the parameters are set up correctly, the free running oscillator will lock at a fixed offset to the one that's injected. That way you can make all the references. Right. Sorry, I should explain that.
But it locks to half the frequency.
Oh, so if it's in, so if the frequency you're locking against is close to your natural frequency, it will lock. If it's double, you'll get subharmonic injection lock. Make sense? Right. Okay. So we've done that. So now we have subharmonic injection lock. And then what you can do is you can couple all of these to each other with the weights from the Ising problem. And then you can actually do a dynamical systems analysis of this. And there's a very famous equation called the Kuramoto equation. If you've ever looked at oscillators, that's sort of actually kind of interesting. It's like somebody just said, this looks right. And kind of turns out to be right. So it's a very nice equation. You can figure out what the Kuramoto equation is for this coupled nonlinear dynamical system. And you can essentially show that the evolution of the dynamics has a Lyapunov function that is, in fact, the Ising Hamiltonian if you do subharmonic injection lock. That's quite elegant. So as far as I can tell, it's the only real theoretical result that gives us any hope that this kind of thing will work. By the way, I'll be honest, we still don't know why it works. Okay, it's still an interesting problem. We are still trying to work on the math, but it's an interesting problem.
So
yes,
so is also Hopfield's network is
correct.
The analog version of it, right?
That's right.
But also has
Right. Okay, very good point. So you're correct. There are many physical formulations you can do that have this sort of time evolution property. And at least for pretty much every other version, I can essentially show it's not really any different than Gibbs sampling and simulated. Okay, with just different time constant. Yeah. But we can get into that if you like. But it's not a very happy result, but it shouldn't be massively surprising because if it was that easy, we'd be solving NP-complete problems all the time.
So essentially, if you can do Gibbs sampling efficiently, you solve the problem.
That's right. So, in fact, even if you just do this naive thing with the oscillator-based Ising machine, it turns out that you also get the same Gibbs sampling type of convergence results. They haven't worked out the math yet, but I think we can now show it. At least the intuition seems to be right. The data matches it if you do nothing. But it turns out that what you end up doing is you end up blending these two injection locking approaches. And it turns out that with that, we get very good convergence results, which we still don't understand why. Okay, so I'll tell you that much. They're still working on it. Yes.
Is there any limitation on the connectivity? Because
yes.
it's like
Fantastic question. Fantastic question. Okay, so this is great. I built this thing, I'm done. So I have a chip that solves one problem. I got the answer and I can throw the chip away. They're not very useful. So you want to have this all be programmable. So that's what we built. So you want to build a graph with your spins as vertices, right? That's your problem statement, oscillators, neurons, whatever your favorite construct is. You want this coupling weight to be programmable, and then we need the connectivity to be programmable. So how do we do all of this? Well, it turns out we already know how to do this. Okay? It's called a field programmable gate array. Okay. And that's kind of what we built. We built a field programmable gate array where instead of a lookup table, we have an oscillator. And the programmable connectivity is my programmable routing fabric. The stats are all different, so you have to re-architect the routing network. It's okay, I've built many FPGAs in my life. I know how to do this. So that's what we did, right? And then you basically, how do you optimize this? If you over-engineer this, by the way, it's totally ridiculous. You never build it. So the name of the game is how do you build an interesting enough programmable network that your problems of interest map, right? And there are well-established ways to do this in the FPGA literature. We use those same approaches to build this for SAT problems. Okay, you can take SAT problems, map them to Ising, you can study the graph properties, and use that to design the interconnection network. So then we did that. Okay. Okay, I'm going to speed up here. Just to give you some sampling of results, these are SAT benchmarks from the SATlib, Timax SATlib benchmark suite. Each of the benchmarks has about 1,000 instances. We use oscillator-based Ising machines as well as a simulated annealing to see how they do. There are 1,000 instances in each. So for 20 variable SAT problems, it's not so hard. Both of them solve all the problems. What does solve mean? Remember, these are all statistical approaches. So we do 100 runs, and then some of those succeed, some of those fail. That's my success rate, right? And solve means that at least one of those runs found the correct answer, found the optimal. It turns out in SAT is a nice problem here because you actually can compute the optimal Hamiltonian. So you know what you have something to shoot for. So you know if you got it or not. Okay. So for 20 variable problems, everything works. We have a better mean success rate. But for 50 variable problems, it turns out that not all are solved with simulated annealing. We solve more, but a success rate is a lot higher. And we normally view the success rate as essentially time. Because the lower your success rate, the more times you have to run this to get a solution. And it's so that's roughly where we are. There are some chips we've built. The different types of coupling and different types of architectures. One of these was designed for networks that were mostly dense in Ising graphs, and this was for something that's more sparse. Okay, so that's the kind of thing we've been doing. So just to give you some flavor of this, you can actually do this. It's not. I said say the jury is out on whether this is a good idea. Okay, as in I'm a chip designer. I can build a SAT solver, not compared to a CPU, right? Which is what everybody likes to do. I mean, to me, the CPU is roughly the worst way you can solve any problem. But the important thing is the N. You can solve any problems, right? That's super important. But if you're saying I'm building something for SAT, then I could build something for SAT. Yes.
And Rajit, does this require variability in oscillators? Would it still work if all the oscillators are perfectly identical?
So if you do require noise.
Something, yeah.
You do require noise.
So variability of this, right? Or
Variability isn't enough. We inject noise. So into the coupling. So there is a noise injection term.
so
Yeah.
then how does it compare against the Boltzmann machine? This is a noisy version of
Yeah. No, that's a great question. So we put SA here. We've tried many other things, and they roughly look very similar. And this also looks similar if I just do the standard subharmonic injection lock. It's only when you do this modified version which blends both of the locking schemes do we get these results. So it's kind of interesting. They're all qualitatively the same, it turns out.
Yeah, but you don't need.
But we don't know why this other mechanism helps. It's open theoretical question. And that's actually what we are working on. I mean, honestly, I don't care about radar anymore. Yes.
Yeah, so we also had a project on these type of oscillators, but using VO2 devices now also.
Oh, okay.
And it's okay to build Ising machine. No? Your input is the initial condition,
Right.
and the outputs are the phases. But now, if you want to scale it up to multiple
scaling
layers,
Multiple layers. So this is
like for example, multiple Hopfield networks that are connected, no, in a hierarchy.
Yeah.
Okay. Sorry.
Nearest neighbor interactions.
Oh no, this is not nearest neighbor. This is fully programmable interaction.
Why?
There is no nearest neighbor interaction. Very little nearest neighbor interaction.
Okay, because
These are SAT
technically
problems.
the Ising.
Oh, forget it. I can show you the degree distribution of the
Right.
graphs and all. This is nothing to do with nearest neighbor.
Okay. But
Sorry.
You started
Hope
with
that opens
Ising.
clear.
Yeah,
That's just to draw a picture that doesn't look horribly messy.
right.
Yeah.
Or if you want to do a multi-layer neural network. no?
Yeah, but this is not solving neural networks at all. This is not for neural networks, right? Neural networks is one way you could solve this problem. It's not the other way around. So, yeah.
The context question, what in here is asynchronous digital?
Oh, it turns out that everything is running in continuous time.
Yeah, but
So the way the communication happens and the way you do coupling between oscillators is done in continuous time.
but are you coupling analog signals?
No, so there's a bunch of interesting papers where we can show that you basically get the same Coulomb, the same Lyapunov function without analog coupling. It's very interesting.
So you have some
work
threshold
that out.
crossing detection and you send
Yes.
events.
Yeah, I mean, it's actually really simple. You can basically send an event
Yeah.
and you can sample it with the receiving oscillator. And you can roughly get the same dynamics. It's kind of interesting. There's a proof of that. Okay? Yeah. That's probably the biggest advance we made in this project, I would argue. That we can do the coupling digitally and nothing changes. Yes.
Yeah, for the injected noise, is the distribution empirical or and also are you using?
They have some patterns that they've seen empirically works well, but this is what we don't understand why it works better, right? So this is what we're trying to
Are you
understand.
using kind of any kind of annealing schedule for your injected noise as well?
So you could view it as an annealing schedule, but the thing is, as soon as you get to the optimal Hamiltonian in this particular mechanism, the thing locks. It's very hard to get it to change. So it doesn't matter too much. But you could view it as an annealing schedule if you wanted to. Yeah.
And what makes this delay insensitive? I mean,
This is not delay insensitive.
No, this is not. This is.
Sorry.
but it still works.
Yes, we don't understand why. As I said, I don't think anyone understands why. The reason I'm working with Rajit, he has the most mathematical understanding of what's going on. That's why we've been working together for a long
It's
time.
magic. Okay.
It's not. And we may realize that actually we're just kidding ourselves. Okay, I could perfectly believe that that's the conclusion. It's just kidding ourselves. We don't see the problem until we have to build a chip that's so big that it's like bigger than the radical, right? So it's possible that actually this approach fails just at a different size scale. That could be, which is a constant factor improvement in my book, right? So that could be what's going on. But so far, at least, that doesn't seem to be the case. But
So how do you program the weights? You compute them previously or
yeah. So based on the Ising problem, you know what all the weights are. You map them to the architecture, and then you're up. Yeah.
you don't train in the loop?
There's no training, nothing. No, this is straight up combinatorial optimization. Yeah. Okay, so that's kind of one of the projects we've been doing. Okay. So I already talked about this. So I'll leave one quote up. So this is a very popular textbook used for introduction to logic design, and this is a direct quote from that textbook. That's roughly how much space is devoted in the book to asynchronous design. But I actually think what they think of as how you should design, how you go about designing asynchronous chips, you should definitely avoid. Okay, so the premise is the conclusion is correct based on the premise, and like most statements, the way to show that they're wrong is to falsify the preconditions. Right, so that's all. So I think there are lots of issues here. We're trying to fix these issues in terms of education, tutorials, and tools. So let me just talk about what we've been working on. We're working on something we call ACT, which is, I put new in quotes because in some sense it's not really new. There are some things that are new, but a lot of this has been known in the 80s and 90s, just never turned into a software package that anybody could use. Okay.
And what's the acronym stand for?
Asynchronous circuit toolkit.
Asynchronous.
Yeah. So what makes this problem hard is a few things. The thing that really makes it hard, I would say, is that there are many interesting design points in the asynchronous circuit space, right? So there are circuits that are very robust, there are circuits that are small, there are all sorts of different trade-offs. I already showed you a very simple example of communication protocol trade-offs. And you could build a design automation flow for a circuit map. By the way, that's what the commercial tools are, right? Synchronous logic. Synchronous logic has a lot richer circuit families. If you ever took a VLSI class, you'll see like 50 different latch circuits, 25 different logic families, and guess what? Nobody uses any of it, right? They use flip-flop based static CMOS. That's it, because that's what the tools support. They don't even support latches properly, right? So like, you think what's the big deal? But I know exactly what the big deal is. So I could talk you through that. But that's the problem. So if you pick exactly, I'm only going to do this. It's not so hard to build an automation flow. But we've designed lots of different chips and we've used lots of different circuits in those chips. And so we know these are all useful. So we wanted to build a flow that can support them all. Okay? And I think we've been successful. So let me try to explain what we did. And oh yeah, by the way, there are non-goals for this project at the very beginning, which is anything that the commercial tools do that we can reuse, we don't want to reinvent them, right? Might as well use that. What's the problem? I don't want to write a spice simulator. What's the difference, right? I don't need to write a layout editor, right? Although I did contribute to magic. But it's more like bug fixing though. And here are actually 1, 2, 3, 4, 5, at least 6 useful design points in the asynchronous circuit family space. There is an incredibly conservative circuit style that works correctly no matter what the delays are on wires or gates.
These are the, for example, there was a chip for the space.
Oh, no. For that, we use QDI.
I see.
Okay, so there's even more robust now. I will pay for how you do that.
Oh, I see.
So there's a QDI control plus data path. Okay, this is very robust. This is what we use for the chip for space, right? Then this is a very commonly used circuit. This is what Loihi uses, by the way. Okay, QDI control with bundle data path. Then this is a circuit family where the only gates you need are already in the synchronous standard cell library. Okay, this was popularized by Philips and a bunch of other places. And then these two are roughly the fastest circuits that anybody knows how to build that work reliably. Okay, so just to give you some idea, the fastest commercial chips, like the N gigahertz processors, which have been hand optimized for 40 years, those run at around 16 to 18 gate delays per clock, and these run at 6. So anyway, of course, you can ask, what can you do with that much pipelining? It's not necessarily that this is a good idea, but it's a useful design point. So this is what the synchronous design flow looks like. I'm not going to belabor this for people who are not chip designers, but there are tools for all of these steps. There's a sequence of steps, turning a behavioral description into gates, planning your physical implementation, doing placement, doing clock tree synthesis, and 2 steps of routing, and then finally finishing up your loop. Right? This is kind of what your tool flow looks like. And the other thing that you should see here is there's timing analysis to optimize your circuit, and that feeds into pretty much everything. Now, unfortunately, all of these boxes are, my clock tree synthesis I can delete since I don't have a clock tree. But everything else here needs timing, and my timing is totally different. Okay, so that's been a stumbling block for a very long time. How do you time asynchronous circuits? So there are some very nice theoretical papers from the PetriNet literature. Oh, yeah. Actually, even from in dynamics in pure math. There's a very nice some old papers. But the only problem with all of those approaches is no real circuit satisfies the constraints that they impose on the problem to do for the analysis to go through. Okay, literally a FIFO doesn't satisfy the constraints. Okay, FIFO with data. Sorry, FIFO with data. Okay. So everything has to be redone. And I want to give you some flavor for how we do the timing analysis, because this is obviously usually for chip designers, everybody's like, how do you do this? It's not very complicated. Here's a ring oscillator. So with X, Y, and Z, we think of this as an abstract graph of signal transitions, right? So if Y down happens, or let's say Y up happens, that's followed by Z down. So Y up happens, that's followed by Z down after some delay. That's how you do it. Technically, you've got this infinite graph of events that occurs as this circuit runs, but because it's a finite circuit, you can show this collapses into a repetitive structure, essentially, and this is sort of the collapsed repetitive structure with this little tick that says I go from the first occurrence to the second occurrence, and so on. Like unroll, like a loop, like an iterative calculation. And given this sort of unrolled graph of events, you can define the time as the maximum time starting from the beginning of time for all paths that lead to my event, right? That's the time at which it's going to happen. So nothing's preventing the event from happening except for the predecessor constraints. Is that clear, by the way? Yes.
Just like in this case, you're guaranteed to have completion.
No. This is just based on the gates.
Oh, the gates, okay.
Right? The gate output's not going to change until the input changes.
Okay.
That's it.
It's like the equivalent of like the timing path. It's these cycles, basically.
That's correct. You're timing
It's a cycle.
Exactly. So, yes.
In the case where you have a couple of inputs, and of course metastability is always a bigger issue in async, and your output, say Z, doesn't give you the desired behavior, and you need to insert some guard.
Okay.
Yeah, how automated is that?
Oh, it's automated because when you do the logic synthesis correctly, this problem doesn't appear. Basically, yeah, this problem was solved before, so the logic synthesis flow fixes that. Okay, yeah, sure. So,
but then it's a very workload dependent problem as well.
Correct.
Yeah.
Yes. So you can do 2 things. You can do the same thing as you do in synchronous logic. You can say, I want to know what the worst case scenario is. What are the different cases? Yeah, that's how we do it. Yeah.
Intuitively, this seems like a harder problem than
Yes.
like the past and asynchronous tool.
It is.
Is the runtime a lot longer?
Yeah, so it turns out, surprisingly, not. There's a very nice algorithm by Dick Karp from the 1980s. And we use it, it's very efficient. There are lots of papers claiming that all these other approaches are better, and like I said, there's a wrong. There's a very nice. The complexity is higher, but the practical runtimes we see are comparable.
So the simulation is sort of the sequential, but then the chip you get at the end is very non-sequential.
Right, but I mean, so it's a very elegant algorithm. In fact, I think this, I don't want to get into that, but since I've like
Harder
2 minutes
problem,
left.
but easy to do.
It turns out it's not that difficult. So we actually have, we've implemented it. It's very good. We had to do some fun data structure tricks to make it more efficient, but this is nothing to write home about, basically. So what you can do when you do this and you have a cyclic structure is you can actually compute this period. So there's a closed form expression for what this period looks like, and there's an efficient algorithm to compute it. And from that, you can compute the timing of everything in your circuit. Okay. I won't go into my language because I don't have time.
The timing problem is solved.
The timing problem is finally solved. We have a sequence of papers that solves this problem fully. The last one being like 2023. And I want to tell you about the last one because that's the one thing I want to at least cover. I don't have time to go into everything in great detail. So anyone who designs chips has seen requirements like this. You have some sequence, you have some signal, and then it goes to some sequence of gates here and another sequence of gates, and then you're like, okay, I need this to be faster than that, or something like that. Okay. Make sense? Those are very, very common things. By the way, setup time is an example of this. Hold time is an example of this. It turns out pulse width constraints, every timing constraint you see can be expressed in this form. Okay. So we have a theoretical formulation now where we can represent all the events in the graph, the event type here, and these timing requirements. And the key result is this universal result that we proved very recently. So this says, supposing I have 2 signal transitions that have to be ordered in time for the circuit to work correctly. Okay. Now you saw that the structure I showed before, think of that as a fork, right? I have a single point and I have 2 signal paths. And we know that this happens before that because the slowest delay here, let's say there's a range of delays here, the max delay here is still faster than the min delay here. That's what I need for the signals to be ordered. Very straightforward. But it turns out you can do more than that. Here are 2 forks where this point appears on the same timeline as this for the same gate. Okay, so you can cascade these forks because you can see by inequalities this happens before this happens before that happens before that. So these 2 signal transitions can be ordered even though there isn't a common point. Okay. So we call these zigzags. And the key result that we proved is if 2 signal transitions are guaranteed to be ordered in your circuit, I don't care what your circuit is, as long as it's digital, then a zigzag pattern must exist between them. So that shows that essentially timing forks and zigzags are both necessary and sufficient conditions for event order. And because of that, I know any circuit that relies on event ordering, I can express with timing forks. And timing forks are the primitive that our timing analysis engine understands. And because of that, we can now do place and route timing analysis for any asynchronous service family. And by the way, even synchronous logic, turns out. So if you give me synchronous circuit, I produce the same timing analysis as the commercial synchronous timing analysis. Okay. So this is a pretty important result, I think.
Yes.
So all of this stuff has been built into a large number of tools. I actually wrote most of the code if you check on GitHub. We've been doing commits. Well, we are writing tools not to write papers, but to design chips. So that's a different standard in terms of code. So we can start from your design. We can do logic synthesis. We can even generate an initial cell library for you that you can characterize if you need new gates. We can export to commercial formats from our flow. We can do Verilog, Spice, or LeftF exports. We call our static timing analysis engine Cyclone. It's fast and cyclic, right? Anyway, we have a physical database. We've got a floor planner, a placer. global and detailed tracer, we have a power routing, and we have global routing. All of these things require timing information, without which it's not going to do a good job. And then for the rest, we always plan to use standard synchronous tools because there's no difference. And because we were expecting our timer to be slow, we parallelize it. This is a lot of these, everything in yellow is parallelized, and that's a joint effort with Professor Keshav Pingali's group at UT Austin. They've got a very nice framework for parallel graph-based algorithms, and that's what we use. Yeah, that's what we built.
Why did you have to write a new placer?
Why did I have to write a new placer? Because it's timing driven. Anything that needs timing. So when I started this project, I won't say which company, but you can guess which ones they are. I approached all the usual suspects and asked them if they were willing to collaborate. And all I needed from them was an API into their software. And of course, they ignored me. When we presented our project at the end of the DARPA program, a bunch of people from the same companies I had reached out to walked up to me saying, "Why aren't you working with us?" I said, "I tried." I actually showed them the email and they were like, "Oh yeah, that's my boss who didn't reply." Okay. So that's kind of funny, or not. But so some of this was extra work we had to do. Fortunately, this tool was a global router that was actually open source that was pretty good. So we started with that, and so this was actually a synchronous tool that we modified. The placer that wasn't in good enough shape for us to do that. When we started the project, we ended up writing our own. Then that's mainly why.
And one more question, sorry. Like, what is your library? What do they actually look like? The cells in the library, like basically.
What do the library cells look like? It depends on what circuit you're using. Depending on your circuit family, you get a different one. Combinational gates look like combinational gates.
Right.
But the state holding gates depend on the circuit family.
But it's the same idea that you have like some timing arcs.
Oh yeah, exactly. Yeah. So for the static timing analysis engine, we even use .lib files.
Okay.
So for combinational gates, it's exactly the same, but for state holding gates, we do something different because we support general state holding gates with the .libs. They support it, but in this hacky way, which none of the tools can really use. Yeah.
Very stupid question, but you use existing PDK, right?
We use the existing
on top of.
Sure.
How do you kind of?
So there is a setup that we do which sets up all the configuration parameters that we need to do everything. That's how we start.
How much of a manual work it is?
This manual, how much work is it? Well, I guess it depends. My suggestion is start with an example and then make changes. It's quite a bit of work. The biggest hassle, actually, I have an undergrad who I asked them to use an LLM to try to generate this automatically by reading the DRC. The biggest problem is the DRC rules. You have like 5,000, depending on which technology you look at, thousands of pages. We have a very short summary of DRC rules that we use. It's a conservative approximation, but I won't get into the benchmarking.
Human,
yes.
It's not automatic.
It's not automatic at all.
But it's linear effort. You do it once and.
Yeah, you do it once per process technology.
Yes, of course.
Once per process technology.
So we have, guys, we can have more discussion later. I want to keep people a little bit of time to go and take a coffee or some more. So maybe we can wrap up.
I'll wrap up very quickly. We have a tool that also allows you to do FPGA prototyping. So we can take our asynchronous design, generate synthesizable Verilog, and run it on an FPGA for functional validation. It's not asynchronous when it's running on the FPGA. You can actually do that, but then your tool is now dependent on the hyphenated version number of the part that you're using. But the last thing I want to end with is this is something that is an ongoing project. So we have a complete neuromorphic architecture in this hardware description language, which is roughly at the same level as a NoE2 design. We've actually benchmarked it, it's better, but that's hopefully this will be ready soon. We have the papers and we've submitted this for publication, and it's under revision now. We hope to make this openly available so that anyone can actually take somebody who wants to try out the neuromorphic idea is going to have a realistic baseline that you can compare with. We read a lot of papers and we were like, looked at all the comparisons and were just not happy. I'm sure all of you have experienced this independently for your own part of the world. But we have a neuromorphic system in ACT. It looks sort of like this. There's a simple example. It looks much nicer now, actually. There's more syntax. And then we also have software. So we can take a neuromorphic system in Fugu, which is Sandia's everybody has their own favorite way to describe neuromorphic designs. This is Sandia's favorite one. So that's what we're using. And we have a mapping where you take your algorithm in Fugu and we can actually generate a bit stream that we can load onto the FPGA prototype of this architecture and run. Everything's there, there's for placement, all of this stuff. My student will hopefully write some papers now, but it works. And the two biggest updates in the last year, I've given a talk about ACT the last
Couple
few
days ago, yeah.
and also a couple of Tellurides ago as well.
Exactly. Yeah.
The biggest changes since then is we've got new logic synthesis. We've got a new way to do this. This is a qualitative improvement over what was previously available. The previous state of the art, which is a company that no longer exists, but there's an academic mirror of their project, which is an open source version. And that's what we compare with. For the same designs, we get a sort of a significant reduction in area, a significant improvement in throughput, and a significant reduction in energy simultaneously. This paper is just going to appear in TCAD. The other thing that's kind of cool is ACT is now object-oriented. So you can have an object-oriented program, you can define data types. Everything is synthesizable. So there's no magic here. I could explain how it does. It literally took me, I did a diff, well, it took me a bunch of time thinking about how to do it, but then it took about 500 lines of code. Okay, so anyway, so that's pretty much the update on the ACT. And I just want to stop by thanking everybody who did the work. Too many of my students spent too many hours doing layout. So there's a group of students. My joke about this is there's a group of students that did all these custom chips when everyone doing state-of-the-art chips was doing custom. Then the complexity got bigger and we were still doing custom chips. So those students, you can tell who they are by noticing that they're not as happy. And then this is sort of the cast of characters that work together to develop the EDA flow. So this was a 5-year project, roughly. And EDA writing tools never ends. Always make them better. So, and then these are the students who are developing some of the new. Kangyan is the one who's developing the neuromorphic architecture. Ole Richter, some of you might know. He's now a faculty member at DTU, but he was working with Elizabeth, the usual community. And then Shariel is the one who's developing the automated conversion from synchronous to asynchronous. And Thomas worked on the Eisen machine. Already over time, so I'm going to stop. Thanks.
Well, thank you, Rajit. Rajit is going to be here. I just make a comment because it's related to the project. We have, it's a comment on the talk. I'm not moderating.
So, we found objects that are quite old, right? 7,000 years old for this zoom from an area that we now call China, right? And what about 43,000 years old for this bone foot from the Paleolithic period in what we now know as Germany? So tens of thousands of years of human activity making acoustic instruments and playing them for what we know as music. How many people here identify as musicians or play a musical instrument at all? Curious. It's like 2/3 maybe. It's greater than a half, maybe half to a little more. And so you will probably know some of what I'm talking about, but also I'm hoping there'll be some surprises for everyone. And then not just music, right? We've been musing about music in a scientific way for quite a long time. And this is Pythagoras. And Pythagoras is credited with coming up with a systematic way of generating a musical scale, right? And this systematic way of doing it was by working with string lengths and tensions, but really everything's notated in terms of string lengths. And he was really excited by a particular interval. There's an apocryphal story. He was walking past a blacksmith's shop one day, and there were two hammers hammering anvils. And he really liked the sound that they made together. It can't be true. But anyway, this is the story. Does anyone know what that sound was that he heard when the two anvils were
Reading.
An octave,
What was it?
an octave?
An octave? No, but close.
It's
It's the fifth. It was the perfect fifth. He really loved the perfect fifth. He's the purest of sounds, except the octave, which is the identity, but twice the frequency. He loved this sound so much. He said, well, what if I kind of do the string length, but it's the ratio that creates that sound of the perfect fifth? It's 3/2. So you have 1.5 times the length of one string than the other. You get this interval of the fifth. And he didn't just stop there. He said, what if I make another fifth? And another fifth, and another fifth on top of that, but transpose them all down to the same octave. Guess what that generates? Does anyone know? 3/2 on 3/2 on 3/2 is a frequency ratio divided down to be in within one octave. Does anyone know what that generates?
A cobra?
Golden ring.
Eventually, it does this. La, da, there's the first fifth, da, second fifth, da, la, da, da, da. Circle of fifths, but actually has a musical scale. It's the major scale. La, da, 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 da. Created only out of perfect fifths.
But all musicians here don't even know what a fifth is.
Well, yeah. Exactly.
Why is that fifth? Very confusing.
2, 3, 4, 5.
Is it octave?
It's 4 steps away, according to this scheme.
Yeah.
La, da, 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 da. It's also born free. It's the same melody. John Williams just stole it and turned it upside down, but never mind. Okay. This is an incredible piece of work by Helmholtz in the 1870s, 1880s. This is the first frequency analysis of musical tones. And it's essentially a Fourier transform, but performed using physical objects, these brass resonators that contain air. And so air is a spring. And so they have a large hole at one end and a small hole at the other. And the idea is, you get a tuning fork or some other sound like a violin or a piano, and you let the acoustic wave enter the chamber of this resonator. This resonator is only going to resonate at one frequency. Due to its size, because air is a spring, it's essentially going to act like a mass spring system and have a resonant frequency. Well, he knows what that resonant frequency is, and if you have a whole bunch of those, then the small hole at the other end, if there's a resonance, it's actually outputting puffs of air. And then he made a little windmill, so you can see how fast it was going around. And so now you play your violin sound or your piano sound, or you sing into it. And using these brass balls, you can tell which frequencies were present, and therefore started to build up a picture of the frequency analysis of sound for the first time.
I have a question on that. Air goes out, but also air comes in on the negative, because
Yes. So the hole at this side is so much larger than the hole at that side. There's an impedance mismatch.
Oh, I see it. Okay.
You get it. And so what he really discovered is that the complex waveform that we associate with the sound, which here, I have to loop this, would be that bottom image is essentially looks like a kind of triangle wave going up and down. He figured out using this technique, this would be like a violin sound, for example. But he figured out using this technique which frequencies are present. And he figured out, oh, it's the harmonic series. The fundamental frequency of vibration. That's the pitch that you hear. We're going to talk about pitch in a second. But there are all these other modes of vibration that are potentially present, depending on the acoustics of the source. But they're always in these integer multiples if it's a musical tone. If there's a fixed string or a fixed length tube, so the constraint is that you have to have nodes at the ends, these are the only modes of vibration that are possible. Okay, so that led to this idea that, well, yes, we can hear pure tones and we hear a pitch, but what about these complex tones? We have the whole harmonic series. Why aren't we hearing all these different frequencies as separate pitches? We're not. We're fusing them into a single sound and only hearing the lowest frequency as the pitch that we hear. So let's hear this and I'll explain it a bit more. So I think we're familiar with the idea of a pure tone. If I just play this. It's a pure tone with a little bit of an envelope on it, something a bit like a clarinet. oddly. Maybe there's some distortion in the system. Now let's do it with 10 harmonics. These are integer frequency multiples of the fundamental. The fundamental is that pitch that's moving around. La, da, da, 2 different pitches, 2 different sinusoidal frequencies. Now let's add a harmonic series on top of those, 10 harmonics. Integer multiples, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times the fundamental. You don't hear 10 pitches. You hear 1 pitch. But what else do you do?
Picture sound.
A different sound, yeah, richer sound. It's got a different sound. The way it sounds is different. We call that timbre. And so Helmholtz started to figure out, using these brass balls, the components of what we think of now as timbre, the way that 2 sounds that have the same pitch sound different. And this is one component of that. Now, things get muddy very quickly, yeah.
But timbre is a little bit more complex.
Yes, timbre is a lot more complex than that, but let's just start here.
Okay.
And we'll start to get more complex, because the more complex is a lifetime's worth of confusion and attempts at understanding. There's an awful lot going on in timbre. So, sing the melody that you hear in this example. Right? If anyone want to volunteer to sing what they heard? Well done. Except that this is harmonics 4 to 10. You know your harmonic series, the fundamental frequency. La, second harmonic first overtone. La, la, an octave above 2 times the frequency, then la. Oh, that's the 5th, which is the 3rd harmonic. La, 4th harmonic, also the octave, then la, that's the 5th harmonic. That's where this harmonic series starts. La, it's not la, it's not la, da, da, it would be la, da, it's actually what's going on at the bottom here. It's not la, da, da, it's a major 3rd above. It's actually an octave, 2 octaves and a major 3rd. So there's information missing here. And we can't just simply infer that, well, we take the lowest sinusoidal component and track that as the pitch that you hit. That's not what's going on, because when we play this, even though it doesn't have the information, those frequency components are not there. They don't exist. It starts on a completely different note, and it's the harmonic series above that. Only has 1 instance of, I think it's 5 or 6 octaves up of the actual fundamental frequency. And it's way, way, way higher than what we're actually hearing as the fundamental note. So the question is, what's going on? Well, some interesting facts. These are all spaced, obviously, by the same amount, because we have integer multiples of a single number, which is the fundamental frequency. Right? So there is some fundamental frequency that's hidden, and these are all spaced by it. First clue. The brain might be doing some kind of pattern matching and saying, well, there's evidence here, because these are all equally spaced in frequency, of a tone that should be here that's causing this harmonic series. So kind of template matching or some other mechanism that's going on that's filling in the missing information to such an extent that you probably don't believe me that that information doesn't exist in the spectrum. It'd be very hard to convince you that the thing you're hearing isn't actually there. Your brain just fills it in automatically.
So where would that be? Where would that be happening?
Well, let's have a look. So this is what's being filled in at the very least, is this lower track is being put there by the brain.
But it definitely sounds higher than the first melody you play.
It's a bit more nasal because the timbre is kind of modulated. That's the timbre, but you're still
You're
hearing.
claiming that we hear the same fundamental pitch.
Hearing the same fundamental
Yeah, I don't buy that.
It's stronger and weaker, but all the studies seem to suggest this is very robust effect, and you can look at it in the neural signal.
All right.
And the brain response, the brain response will tell you you're hearing that pitch.
A century of work.
You
You don't believe it when you read it.
I mean, it sounds higher to me, right? So it sounds like.
It's brighter
timbre
for sure,
brighter, it's
yeah,
brighter, okay.
because the timbre is kind of causing it.
Right.
Yeah. It's sort of more pinch, yeah. All right, let's do a little bit of neuroscience, right? Because I promised you some neural correlates. We don't have a huge amount of time, so let's see what we get. Brainstem, midbrain cortex, and these are slices, obviously. And so roughly, I've simplified the diagram a lot, but roughly we can kind of think of, you know, you have coming in from the ear through the cochlear nerve into the cochlear nucleus on the, let's say this is the left-hand side. Part of the signal will continue on the left-hand side, but actually what's really interesting is mostly it crosses over to the right-hand side immediately, right at the brainstem, and you have this superior olivary complex, or the superior olive, which is the first kind of brainstem area that has been studied widely. It does all kinds of things we'll get to in a minute. Then we go up to midbrain, and we're interested in the inferior colliculus. So we see this ascending pathway, inferior colliculus here. And then we go up to, you know, the medial genicular body of the thalamus. And a lot of stuff goes on here. And only then, after that, we go into auditory cortex, primary auditory cortex, sort of sitting closer in. And it's in superior temporal gyrus, somewhere in Heschel's gyrus, the transverse temporal gyrus. And that's where cortical processing starts to happen. But before we get up to the cortical processing, there's all these stages of stuff happening in the very fast responding, very ancient brainstem and midbrain, right? So you can look at all kinds of animals and see all kinds of things going on in these regions. So let's sort of take a look roughly at what's going on, kinds of things that might be happening in each of these stages. So very early on, the superior olive or the superior olivary complex is processing sound localization. Where's the sound coming from? Right? You hear it behind your head. That's interesting. For all kinds of reasons. That's being processed almost immediately right here. Very fast response for sound localization. And what does it need to do that? It's processing signals from both ears. So you see the signal from the left ear goes in here as well as the crossover as well. But signals from both ears are being processed somehow. And two kinds of information are helping with spatial cues. It's actually many, many more kinds of information, at least three that are really important I can think of. But the two that are being processed here, interaural time differences. If I have a sound coming from that location, the wave is going to hit this ear before it hits that ear. There's a time difference between the two. It's the same waveform that will arrive at different times. So if the brain can process the time difference for an equivalent signal, it has some useful information about spatial.
So this is azimuth only.
Yeah, azimuth, right? Yeah, elevation is done by
Because we get the P9.
the shape of your ears, which is a much more complex thing that I won't get into. But then there's interaural level differences, right? How much louder is the sound on one side than the other? That's also a cue. It turns out that time differences are really only good for low frequencies, because at high frequencies, the phase gets very hard to track and lock into. And so you don't understand differences between phases much at very high frequency, right? But at low frequencies, certainly interaural time differences are very important. At higher frequencies, the level differences become important. But these are basic cues to spatialization. There's also reflexive responses, the acoustic reflex. If you've ever heard a shotgun going off and you jump, that's the acoustic reflex. And there's all kinds of them. Right? So we have startle responses and all kinds of reflex responses to sound. That happens right here, basically in the brainstem itself. Okay, obviously it's a very, very fast responding circuit and it's connected to the motor system because it makes you kind of startle and jump, right? So all kinds of things that happen.
Question.
Yeah.
So does the system convert the level into time, or how does the level work? Because you know there is a cubic.
Yes, too much detail for that.
Too much. Okay.
But I'd love to talk to you about it.
Okay.
Okay.
Yeah, thank you.
And then there is temporal processing that goes
Okay.
on here, right? And that's timing and phase differences in the sounds, essential for understanding speech and rhythm, all kinds of cues about which arrive first,
I see.
masking, like if something arrives first and something arrives right after it, ignore the thing that happens right after. That might be a reflection off a wall, not as important as the primary signal.
Okay.
All kinds of things happening in it. Okay, let's go to the midbrain and talk about the inferior colliculus. And this is sort of a main auditory processing center. And a really important concept that's maintained throughout this pathway and is particularly preserved here and passed up is the idea of a tonotopic organization. Can someone, because I'm already out of breath, tell me what tonotopic organization is? Thank you.
It's the spatial mapping of frequencies.
Spatial mapping of frequencies means that the fibers that are coming in this afferent pathway maintain their spatial relationship that corresponds with frequency. So as you go from low frequency to high frequency, a spatial relationship is maintained. It's complex and it ends up in the auditory cortex. Primary auditory areas are also tonotopic. So you can actually map, but if you play tones at different frequencies, you can kind of see where those tones end up spatially in auditory cortex. It's a very complex process because of this fusion for hearing frequencies as a single sound. If they have a harmonic series, for example, it's not just about single tones, but basically this tonotopic organization being maintained. There's also the idea of multisensory integration going on here. So information from visual cortex or somatosensory or motor feedback is going on here as well. And then this idea of the external cortex, sound localization, binaural cues are coming in here. This connects to the visual center for obvious reasons, right? If you hear a sound coming from over there, you might want to check to see if it's the lion jumping out of the bush, right?
So is there learning happening here?
Ah, good question. A lot of this, I mean, I know that there is learning and there are studies that are going on here, but a lot of this is automatic circuitry.
Automatic, so not really, okay.
But there is, but we'll see that learning is involved, and you'll see why primarily in a second. But then let's talk about the MGB, the medial genicular body. So I'm just sort of focusing on, you know, one area per kind of stage, if you like, just so that we have some language. And the medial genicular body is really important, right? Because this is a relay station. It's the final substation of kind of lower processing before you go up into cortex. And this happens in the thalamus. And it does all kinds of auditory feature processing. It's going up, radiates to the primary auditory cortex and superior temporal gyrus. But the neurons here are actually tuned to specific frequencies and temporal patterns and frequency patterns. I mean, a lot of this is Shihop's work. Not only timing and onset timing and relationships between onsets and things like that, but modulations, the thalamus, the MGB and the thalamus tracks for each frequency component in a sound. How is it changing in time? How is its amplitude varying? How is that component varying in frequency? Do you know what vibrato is? A singer who adds vibrato is adding expression. That's frequency modulation. Okay, and there's all kinds of other effects in music, you know, amplitude modulation, other things that can be tracked from here. And there's a selective attention and gating that's happening here. So kind of more complex feature-based processes that are trying to select important features and pass them, group them and pass them up to the cortex. Okay, so this is a really nice picture of bottom-up processing in the auditory system, right? You've got, okay, you have these really low-level things going on. You need to know where the sound's coming from very rapidly. Is it a dangerous sound? You need to know that rapidly. That's down in the brainstem. Midbrain, you're starting to organize your features and start to get timing information, group frequencies, try to understand what the important features of the sound, pass them up through the thalamus into the cortex, and we start to build up a bigger and bigger picture of what it is that we're listening to and where it's coming from. All right, now let's break all of that and say that none of that's actually true, right? But we can't possibly be processing in a bottom-up fashion for all kinds of reasons. It can't just be bottom-up. That is going on, right? And our reflexes are definitely based on that. But there's also other information that's coming from the top down, and we need to account for that. So let's look at some familiar ideas from music. So here's pitch class circularity or octave equivalence. So if I sing a tone and another tone, la, la, are they the same pitch? No. La, la. My tenor is a little off today. La, la. Nearly. Are they the same pitch? Pitch back.
Maybe.
Oh, maybe.
Yeah,
What is
maybe.
louder? They're the same pitch class.
Yes. Yeah.
Humans are possibly the only species that hear two frequencies that are related by a power of like 2 to 1, 4 to 1, 8 to 1.
Really?
Two frequencies that are related like that, they hear them as equivalent in some way, and that's via the pitch class. So what is pitch class is where we take the octave, which is the 2 to 1 frequency ratio, we divide it into steps. Those steps are somewhat like what Pythagoras was trying to do, right? Find all these ratios that create discrete steps that divide the octave that make a scale. Here's a chromatic scale, which is just all 12 chromatic notes that we use in music and Western music. And if you go around the circle, it's going to continually increase in height. La, 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 la. You see where I'm going with this? It's just going to keep going up and up and up and up. Except that the pitch we perceive, meaning the way we think of the melody, the note that we're thinking of, behaves more like this. Is that when we come full circle, we hear at the next octave up, after we've gone all the way around, we hear something that's equivalent, and that's the pitch class.
But there's something here which is not fully scientific or quantitative, and that's the idea of aesthetics. What is the method? Why does it sound good?
Well, we'll get to that.
No, okay, but you know what I mean?
I don't, yeah, I do, but let's just stick with octave
Okay.
equivalence, because that's a human trait that I don't believe has been observed in other animals.
Okay.
Someone tell me if it has. I don't think so. Octave equivalence.
Birds?
Don't
know, base.
Some
You have to
monkeys.
ask them, yeah.
Yeah, I don't. So, but I could read somewhere that this it's possible that humans are the only species to do this, but I don't actually know. So anyway, we can actually create the effect of the barber pole or the Escher-like staircase, right? By doing a trick in frequency where at the edges we kind of fade in. So if we go through, if this is a harmonic series for steps of the scale, so these are sine terms. So this is a frequency analysis, frequency time, and we're seeing these scale steps. So we've got a complex tone with 3 harmonics going on. And you can kind of see I'm fading in the lower one here, and we're fading out the upper one. And so as you kind of do this as you step up, effectively what you're doing is you're getting rid of the high components and bringing in the low components slowly across the whole scale. And if you do this, you're essentially getting rid of the notion of pitch height, and you're only left with pitch class. That's the idea.
Mm-hmm.
And this is due to Roger Shepard from 1963, because really he recognized that, well, really pitch behaves like a helix, where you just keep going up and up and up, but when you're in the same azimuthal point, you're hearing the same pitch class, but an octave relationship. But if you use these Shepard tones, which kind of disguise the fact that the harmonics are constantly going up by doing this barber pole effect, you can collapse the whole thing down just onto a circle and hear a continuous circle rising. And so this has been used by composers like Jean-Claude Risset, but let's just hear a kind of a simplified version of this. And then the lowest one. It's going to go up infinitely. It's really just back to this. You didn't notice that. That's a nice illusion that allows us to kind of hear that. Yeah, we can hear pitches arranged just in a circle. And sort of neutralize height out of that. Except the local effect is good. Kind of interesting too. Here's another example of where octave equivalence maybe breaks down. Okay, Diana Deutsch, famous music perception researcher and music perception cognition, wrote a book called Music Cognition in the 1980s. And Diana Deutsch, here's an example of a melody, and if you recognize the melody, just put your hand up. recognize that melody?
No, it sounded
No?
video game.
It sounds like a video game. It's not Mario Brothers. Is it what?
The ode to joy.
Oh, to joy. It's not, but I could actually hear what you meant there. Yeah. It's interesting because this challenges the idea of octave equivalence. If you're jumping around and you're moving around that circle, but you're also moving up and down that helix too rapidly, well, the brain can't track in it. And so let's actually hear what the melody was. Yankee Doodle. Now let's go back. Check your perception.
Now we get it, obviously.
Right? And you wondered why you couldn't hear it in the first place, right?
Like Europeans don't know that melody, right?
So if you're European, if you're not American, that might be tough. That's right. But we can extend this idea, like the idea, we think of source localization. We think of being able to track. Many people are interested in the idea of source separation. Oh, I could just take a recording of two violinists playing their different melodies, their different lines. And I can do some frequency analysis, and I can do my signal processing, and I'm real smart, and I can extract those two melodies, and I'll get what violin one's playing, and I'll get what violin two's playing, and I can recreate the score from that, right? It's the kind of canonical problem in auditory scene analysis, is how do I take multiple streams of sound that are going on simultaneously, separate them out into separate streams. And back in the 90s, we were all trying to do it with signal processing, and machine learning came along, and we tried to do it with that. It's the rocks on which many a PhD thesis were dashed. And now we have deep learning, and it seems to have kind of solved it, except all is not what it seems. Again, and here's an example of that. I'm just going to play this starting at 14 minutes.
Some of the illusions I'll be playing need to be
That's Diana Deutsch.
Melody, right, Jim?
So we'll see that there's two melodies
Some
here.
of the illusions I'll be playing need
melody, right, Jimmy? You're going to do it 4 times, then Josh.
Can you see those two melodies?
4 times, and
One kid's going to play the top melody, one kid's going to play the bottom melody. So let's hear them.
Okay, audience members, please be quiet. All
Kid number
Jimmy,
1.
1, 2, ready, go.
Right?
Okay, good. Let's keep out those hesitations, all right? All right, Josh, would you play the red melody
Now,
4 times by yourself? Ready?
Kid number 2 is going to play the other melody.
Good. Now, listen carefully, everybody.
How they're going to play them together. If you can hear those
Try
two.
playing them together 4 times through. Concentrate on your pattern, not the sound. 1, 2, 3, and 4. Stop. Did you hear it?
What are the two melodies that you're, what are the two melodies that you're hearing?
Harmonics. No.
It's not harmonic. There's pitches.
The pitch, yeah.
Pitches derived from harmonics. They read the silent mode, sure. But what are you actually hearing? You're not hearing what they were playing individually. It's all
pitch pattern.
You're hearing one going la da da da, la, da, and the bottom one's going la da da da, da. What's going on? They were playing the thing you first heard, which was like dum 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 dum. It's something completely different. When we played them together, you heard that.
Is our brain picking choosing between the two and joining them?
It's joining them. It's a Gestalt principle. It's like it's much easier to hear closer notes as forming a kind of stream of melody than to have the notes jumping around and crossing each other. Even though one kid's just playing the xylophone, you could attend spatially. So it turns out it's really hard to attend spatially. Even if you do this in headphones, your brain will force you to hear the phantom melody in one ear and the other phantom melody in the other ear, instead of actually what's being played in both ears. And so something both very high level, top down, is going on at the same time as something very low level, where your spatial perception is being altered by what the brain thinks you should be hearing, rather than what's actually being played. So this is the reason why auditory scene analysis is impossible and will never see the light of day in terms of orchestral music. There's a beautiful example here of Tchaikovsky's Pathetique Symphony No. 6, the last movement, where in the opening, he did exactly this trick, thinking he could throw the melody across the orchestra between the first violins and the second violins and have them jump around. The audience would hear this incredible spatial effect, except they don't. They just hear something like this, and it just sounds like he orchestrated two simpler melodies. And so the illusion dominates over what he tried to write.
So even if you perceptually modify the delays to enhance the spatial separation,
there are things you could do
to actually trick that.
and you're on the right track, right? You could use Gestalt principles to modulate this. So here's the idea then, that clearly the world is organized. It's full of patterns. And if the brain is going to use anything to understand the world, it might as well use a fact. The fact of the patterns in the world. And the facts of patterns in the world for auditory signals tends to be things that are more closely related in frequency tend to belong together. Things that are most closely related in time tend to belong together, etc., etc. And so there's a dominant effect, probably from learning, to get back to your point, right? That actually has an efferent pathway that then affects all of the lower brain processing. So this is very interesting for auditory science. It turns out, I can't remember what the ratio is, but there are something like an order of magnitude more fibers coming down than there are going up for many of these pathways. So there's clearly a lot of top-down control.
So is this the equivalent of the proto-object in vision? And I don't know. I mean,
Here's a paradox also by Diana Joyce. It's her most famous one, and it's worth hearing. If you split the octave in two, it's called a tritone. Why? Because it's a whole tone. La da la la. It's three whole tones away from where it started. La, 1, 2, 3. La la.
It's a whole tone and octave.
Whole tone is one step. The first step of the major scale. La da, do it again, da da, la da, la. There's your tritone. It splits the octave exactly in two. So if I use a shepherd tone, so I've neutralized pitch height, and I play two tones that are a tritone apart, and I've used a shepherd tone that neutralizes height, it's completely ambiguous which direction it went. It could have gone down by half an octave or up by half an octave, because they'd be exactly equivalent because of the profile of the shepherd tone. And so let's listen to this. You're going to hear it 4 times in different orders. And raise your hand if you hear it going up. But don't raise it if you hear it going down. And there's going to be 4 presentations. So those who thought that went up, raise your hand. It's about 30–40% up. Yeah, if you thought it went up, raise your hand high. It's about half, a little less than half, but about half. What about the next one? Did that go up?
yes.
Look around. You're not in agreement, people. And again?
Overlapping. Is it non-overlapping?
I don't know. I didn't. Up. About half. All right, so the illusion holds. About half of you hear it go one way, and the other half are hearing it go the other way. But here's where things get really weird, and some of you know this, right? Is that, do you know that this effect is actually biased by the language that you speak and grew up listening to?
Really?
What does it say? What does it say percentage at P?
So this is where basically where there's some distribution here that basically measures where you're most likely to hear the effect going up. And it's different for people who speak Californian English than people who speak Vietnamese. It's also different for people who speak Southern English from England than people from California, it turns out. But there's a change in how you hear the direction of 2 tones when they're presented with that. The details of this graph may be a little complex. I don't want to get hung up on it, but you're right to question Yeah, what does this mean? I was trying to read through the paper and I couldn't quite get all the details, but I do understand that this distribution is to do with where the peak effect is, whether it goes up. All right, I'm going to switch from pitch to rhythm, and then we're going to go to timbre. I've got about 20 minutes left, right? Fred Lertle came up with this sort of nice notation to explain what happens in rhythm. So it's quite easy for you to track a rhythm, right? You do that again? Right? Tap your foot where you think the beat is. Right. You notice something really important. What we think of as the beat occurs in places where there's actually no sound. The beat's not in the sound at all. The beat's in your head. It's all in your head. It doesn't actually exist in the signal at all. The beat is a neural oscillation that you're in training to at a particular frequency, the evidence of which is being provided by the rhythm. But you're sustaining an underlying steady isynchronous beat to interpret what you're hearing as rhythm. And that's why I can create a rhythm where no part of the rhythm is actually on the beat. You still very strongly feel the beat, almost as a motor response.
The beat is just start popping though, right?
No.
Oh, it's not?
So rhythm and beat is different.
Beat is where you would tap your foot. Right? That beat had no rhythmic component. So that's very important as well, right? That your head is creating at least a half of what you're perceiving as rhythm. Because you've had the actual surface rhythm that's coming through your ears, and then an internal reference signal is created by a neural oscillation. Okay, so this is important, but it's interesting to see then, okay, if we have this, what are people's internal dynamics, their natural kind of resonant frequencies for perceiving beats, if we have a tendency to want to fit everything into a constant oscillatory rhythm and reference it against that. That's what we call meter versus rhythm. So let's do this experiment. You're going to hear a constant rhythm. Here's what I want you to do. I'm a music professor, so this is conducting class. Very soon we're going to have a listening test. And so I want you to close your eyes and conduct to the rhythm that you hear. Just conduct, right? Tap your finger where you think the beat is. Close your eyes. When I keep, then once you've settled on it, sustain that, keep going, and then I'll tell you to open your eyes and look at what everyone is. Okay? So close your eyes and use your finger to conduct the beat.
Can we count inside?
You can count inside your head if you want. Just don't do 7 or 11. 4 is good, or 8. Okay, here we go. So close your eyes, I'll tell you when you can open them. Now, keep going. Open your eyes and look around the room. Where's the beat? Who should I ask? You all have a different idea where the beat is. But you all have a different natural kind of resonant frequency in which you tend to feel the beat. And it might be related to your gait speed, due to your size, the beat of the movement, all those kind of stuff. The physics of your body. Music's directly coupled to your motor system. Oh, and how you do things, how your body moves. You know,
That's great, yeah. It's very close. Was there a ground truth on those?
No, because it's isynchronous rhythm. So there's actually no emphasis on any one of those tones. No beat actually was emphasized. So you could just put it wherever you want it.
Okay.
But it's just interesting to kind of be an engineer and just hit the system with an impulse to see what comes back. Right? So I kind of got the impulse response from your systems in a way. You know. So we can measure rhythm using modulation spectrum. So the idea here is that cochlear channel sort of representing frequency, and we understand tonotopic organization of frequency components. We saw the harmonics that belong to a pitch, and they were fused together to make a note. We're tracking the fundamental frequency, but those frequencies are not constant and stable in time. Those components may be varying in frequency, and they may be varying in amplitude. And those are very important pieces of information for speech and for music. This is Shehoff's work. There's an awful lot of work on modulation and going back a long time into the 80s and 90s, right? And what we're looking at here is, this isn't taken from Shehoff's work, the same as like a lot of his work is. But here, these are frequencies that are actually frequencies of variation at a given component frequency. So if I have 1,000 hertz tone and it's varying at 4 hertz in its amplitude, right? It would show up here. This is the amplitude modulation frequency. So I can start to see for different rhythmic components of music, I can kind of see peaks in the modulation spectrum. It turns out that the thalamus is tracking this information. It's tracking modulations in amplitude and time, amplitude and frequency. It's a very important part of the feature set that's been passed on through the auditory cortex, and something that has been underused largely in the engineering community so far. It's started to be used more and more. But something I think several of us are curious about, and there's some projects going on here that include modulation spectrum. There's been some beautiful work by Keith Doling, looking at the ability of musicians and non-musicians to neurally entrain to rhythmic information in piano music and other kinds of music. It can be modulated by the actual timbre of the piano. If it has a softer attack, it evokes an oscillatory response. If it has a harder attack, you get a tension response. Because every time the note attacks, you're re-triggering the auditory attention mechanism. So you get different neural responses depending on what the shape of the sound is in time. I think I need to move on. Please save questions for the end, otherwise I won't get through it. So now is the listening test, as though I'm a music professor. So this is typically what we do in an intro music class. It's a drop the needle test. So imagine all term we've been listening to classical music. And it's all these different pieces. And now I'm just going to randomly pick one, drop the needle on it. You have to tell me the style of music, the year or decade it was composed, who the composer is, all right, and what the title of the work is. So I'm going to give you these musical excerpts, and you're going to tell me this, right? So everyone ready? Here's your first excerpt.
Huh? Oh. You have to hear it again? Or not? No.
How much tuition?
That was the music. Can you play it again?
I think the rap.
It's rap. He got the genre right. That's got a rap in it. Yeah, you got the genre right.
It's 80s.
No, 80s.
Non-classical.
80s.
I think 90s can do it.
It's non-chorus. Let's listen to the chorus. That's from the right. Let's play it again, but it's different excerpt, same length. It's 400 milliseconds. I have 300 millisecond versions as well. 400 milliseconds, same piece. Decade, style of music, correct. So now you can infer the decade. What is it?
80s. It's 80s.
Right. Hold that thought.
80s.
Same piece from the chorus this time.
Yeah.
Who recognizes it?
Yeah.
Well, this one's pretty-
Late 90s.
Yeah.
Early Outcasts.
Yeah.
Kind of rap, hip hoppy, poppy. You didn't get the melody.
We didn't hear the name.
Outcast. With a K.
Outcast, okay. Oh, Outcast, okay.
How many of you got that? About a half. It might be age related. And I'm going to say nothing more about it. Here's another one. Not from the chorus, so from the verse.
Yeah.
Right. In that clip, you had an interval, so you have 2 notes. Okay. So you name that interval. But the point here is, with a single sound, you had no melody, you had no rhythm in that verse, right? Single sound. more than half of you could tell me exactly what that was. It was less than 400 milliseconds of information. Is that cortical processing? It's some very fast loop between the early stages of processing.
Well, what does imaging say? I mean, when it's imaged.
It's a good question. I don't think we've taken these clips of real imaging on.
Is this how Shazam works?
No, Shazam needs audio landmarks in time. So it needs time. We have very little time here. We have almost no information about it.
Is that right?
So the way it sounds, the timbre, right? Just a single note, the way it sounds, the timbre has entirely identified.
Well, can you play the last clip then?
This exact piece.
So this is so timbre, you're saying?
It's basically, this is timbre.
I see. Yeah.
That's when he comes in screaming in the chorus, if you know the song. Okay, I'm going to move on because we are running late on time. So let's talk about emotions, right? So this idea of autobiographical memories, that pieces of music that you heard in your youth are so deeply encoded within you that if you hear a few milliseconds of the sound, a single note, not even a single note, you can immediately retrieve that and you know what the song is. You don't even need melody, you don't even need rhythm, you just need the way it sounds. And it's not the sound of a particular instrument or even the voice, right? Although in the second example, there was the guitar and there was the voice. The first example is a little bit more nebulous. It was just some drums and maybe a little bit of voice. Got it right away. Why is that happening? It's some interaction between these midbrain responses that are very fast and the thalamic going into hippocampus, kind of pulling stuff out very quickly and giving you an identity. Why would we have the ability to recognize a sound so rapidly? Survival, right? Yeah, you're gonna need for some sounds if you really want to know really quickly what it is. We have that ability. It's incredible. That comes from lower parts of the brain and midbrain.
And that's 500 milliseconds. That's really on the 500.
400, less
400, yeah.
And we can do this with 300, 250 milliseconds. It still works.
Whoa.
Lesser effect. This work is by Carol Krumhansen, called Plink, paper called Plink from 2012. I started working on with her on brain scanning these clips, but I didn't finish that work. I'd love to finish it. Another project we could do. Here's a piece of work I did on music and emotion that actually is kind of neurally based with Bo Sievers and Talia Wheatley at Dartmouth. And this was the idea. We wanted to see if the emotional response to musical melodies had some kind of underlying code. That if a melody had certain features, would it evoke reliably a particular emotion? But not only that, if we're talking about neural codes, what if these neural codes are more general than just one modality? But if we figured out a neural code that if you could create a melody from, but from the same code, create an image from, an animated image, could you play from the same time series sources that were parameterized for sound and animation? Could you play those to populations, different groups of people, and have them recover the intended emotion, perceived emotion? So that's what this is. So one group of subjects were given these 5 sliders that were just, look, here's an underlying rate. Imagine the isynchronous signal. That's the rate. Here's the jitter. How isynchronous is it? There's a lot of jitter, it would be. There's not much jitter, it would be. Right, that jitter, there's a bit of jitter. Consonance or smoothness. This is like how close to a musical scale that sounds aesthetically pleasant is it?
Yeah.
Or how kind of dissonant is it?
I think so. Yeah.
But in the graphical domain, it's like how crunched up is this ball? The ball's moving, it could be moving smoothly, it could be jittering, it could be crunched up, it could be smooth. Just creating analogies. And then the step size is for each note in the melody, how big a step is it taking? Is it nearby, so it forms an easy to perceive melody, or is it jumping around, which forms one of those phantom melodies maybe that are hard to track? And then an overall direction, is it generally going up or down? Using these 5 components, one group of subjects were given a set of target emotions to set the sliders to generate melodies. Another group were given target emotions to generate with the animation using the sliders. And then I'll come back to that. Then two more groups were told to listen to the music that was generated and to look at the animations that were generated and see if they could recover the correct emotional category. It turns out with 100% accuracy, every single subject could tell you out of 5 emotional categories which one was being communicated by the sequence that was generated from the sliders, either as sound or as animation. I don't have time to play these.
What are the 5 categories? Just quickly in words.
It's
Happy,
sad, peaceful, angry, something else.
This must be very cultural.
Thank you, Shihab. So they took this experiment on the road to a remote part of Vietnam, which had very little contact with the West. It was a 3-day hike from the road, from where the bus dropped, and they had tents and everything, and they went to this village called Curran. And this was published in PNAS in 2013. So Creon. And they had to learn, we had to set them up with a different kind of interface because they weren't familiar with Western keyboards and stuff, but they basically did the same experiment. Generate melodies that sound happy or sad or joyous or peaceful. And then what was really interesting, and the same thing with the animations. Then what was really interesting is to take the different groups from the different cultures and play back the sequences to the other culture to see if they could recover the same emotion. And with a high degree of statistical significance, they did. And so the paper is really about that music and movement, because you have movement in the animation, support an underlying neural code, right, that has universal expressive capability across cultures, which is pretty interesting. So there's this whole thing about what's learned and what's built in and how innate are these kinds of emotional responses. Infants, mothers have these kinds of things too.
I mean, that's kind of what this with the, you want to be very careful with this type of playing than saying, you know, we all perceive, you know, these two kinds of people.
Yes,
You know?
and this particular basis set and this particular set of sounds and animations may be just way oversimplified, but it's an interesting result.
I am in support of this thing, and I think it's valuable, and there's some truths about this universal neural code, but I just think that actually would be better for a scientist who undertake this research to be very cautious, because otherwise we get attacked on.
You're absolutely right.
I mean, it wouldn't be news if they didn't find this, right?
What?
If they didn't find this, it wouldn't be so interesting. So it's a little biased. Actually, it's the other way around. No,
What do you mean?
that it's universal is kind of like interesting.
I'm actually going to stop there
No. Anyway.
because I'm running out of time, and I think this is going out on a high, and the next thing's not going to add anything. So let's just stop here. Thank you, and I'll take any questions.
Back to the very start of why do you think the brain does that? Why does it infer this lowest base frequency? What is the advantage? Yeah, because the low frequencies, the high frequencies are blocked, and noise is usually attacks them. Why would we infer the lowest frequency?
And does it occur in nature and outside of music? You know, does it occur?
Well, in speech.
Yeah, or in
So
speech.
the fundamental frequency that you're tracking is exactly the same principle here. And so speech doesn't need music because I can just do it like this. It's okay. It's a sense of frequency. It's natural.
With perspective, yeah. So you showed some incredible experiment. This 500 milliseconds to me is just fascinating. Has anybody done this experiment where they take the super multimodal LLM and just give the machine 500 milliseconds and see what it can generate?
That'd be like, you know, a couple of tokens worth of. Yeah, I don't know. That's really interesting.
Is it gonna work at all? I mean, it's a.
I bet Shazam can.
No, Shazam, no. I mean,
With 500 milliseconds.
500 milliseconds.
It needs longer.
Well,
Humans
humans
can.
can try. Separate tone.
Okay, someone should try Shazam with 400 milliseconds.
Those are automatically
Well, the difference is though that you're doing an exact signal match, right, in the presence of noise. So if the signal is the same as what you're storing hashed on your server, and you have the ability to be robust to noise, locality sensitive hashing can do that and other kind of thing, then you'd still get an exact match. It's a question of how much time do you need to get the match. But it's clearly doing it a different way.
So do we actually try?
Well, I don't think we have time right now. We should do it offline afterwards for sure. Yeah. Yes.
But I imagine that it makes sense to have some sort of like artificial invariance that things sound similar, even though like if you just look at the spectrum, it might look kind of different, but because they are like we talk, we sound different when we produce speech. So maybe you want to be able to recognize that these are the same sounds, even if the people who produce them, like make different sounds. So it's like artificially grouping stuff together. But like that explanation would make sense to me. But then I'm wondering, like, animals that don't use sound to communicate, do they have similar properties? Like, do they also feel that sounds are similar, or like is it a language thing, or because I also don't understand why would the brain go through all of this effort of mapping different sounds on kind of the same perceived
Well, I think what's going on here, to go back to Toby's question, and then I'll get to this, is that this is how the universe behaves. If you have fixed length anything and you kick it, this is how it behaves. It's how it behaves at the quantum scale. This is how it behaves at the scale of the entire universe. The boundary conditions, right? There are basically harmonics spread across the distribution of galaxies. Right? So this is just a fact. It's just a fact of how frequency components behave when you have fixed length entities, right? Water behaves differently if it's dripping into a sink, right? You have tap dripping because the cavity that's resonating will change shape as it penetrates the surface. It might get bigger. You get more, you get these, and then it will get smaller. So that's non-fixed. But if it's fixed, you'll have a constant harmonic series. So why wouldn't you just, because of noise and all the rest of it, why wouldn't you just fill in the masked parts? Right. So it's just a habit from filling in because stuff gets masked in the real world by noise events, which could be other animals or trees or wind or whatever.
Yeah, I just want to follow on the question with another question. So what's the relationship of this to Mel scale?
I didn't talk about,
Yes.
So the only place really that came up is when I talked about cochlear channels later on, which I didn't really talk about. That actually the way, so if we look at these frequency transforms, they're linear, linear frequency. This is not how the brain works. This is hertz.
Yes.
We have channels that are logarithmically spaced in range. And so we have much denser neural detection and coding for low frequencies than we do high frequencies. And so the bandwidths, which are kind of being sensitive to frequency, get wider and wider and wider exponentially as you go higher.
But do they have does that physical, that construct affects the perception here in the music? What you do here?
Actually, it does. And as an engineer, if you're working with music, you'll usually put music on a logarithmic axis because then the picture will look much more like what you hear.
Oh, I see.
But I didn't want to get into all those details. But very important that we actually perceive pitch logarithmically. Here's the evidence for that. Have you ever looked at a grand piano? Grand piano takes equal steps, right? In the white keys, for example, it's not quite true. But equal steps on the white key.
I've never seen a piano other than logarithmic. Grand or no grand.
Right. So it's then logarithmic, but the shape of the actual piano is an exponential curve. What's that about? Well, it's basically the high frequency strings are exponentially shorter than the low frequency strings. But the distances you move for perceived intervals of pitch are linear, right? They're constant. So it's a mapping from linear to exponential. So you can actually, if you put the piano, turn it upright on the stage, you can show this is my graph for music. What a grand piano is. All right, very good. Okay, I think we need to stop there because we're at time, but
all right, I do have recorded videos of similar things on this, so I apologize that I didn't start the recording in the beginning of this, but you're still catching the beginning of this talk. All right, so we have this sort of really basic component. I am terminology-wise, I'm going to say, hey, this group, this set of weights here we're going to call an encoder because it's taking data that we're feeding into our network and turning it into some sort of neural activity. So this is the encoder set of weights. Again, it's just a set of weights, nothing special there. And then this set of weights here, I'm going to call a decoder because it's taking the neural activity and it's decoding out some information. Okay. So yeah, that's just labeling things in any particular way. And then again, so one thing in a normal sort of minimal thing I might do with a neural network is just simply say, all right, hey, if I have some input-output pattern X, I want some function, I have some X data that I want to turn into some Y data. I don't know, the input is images and the output is this a cat, is this a dog, whatever, something. That is a function. And one of the typical things that one can do is train up these find the weights that best approximate a function that you have. And I'm happy with people using any method they feel like to do that. If you feel like doing that with backprop, go for it. Honestly, for models this small, for networks this small, it's just as easy to like randomly generate this set of weights, these encoder weights, and then optimize for these sets of weights, the decoder. And the nice thing is, if you're optimizing one set of weights, you don't need backprop. This is now a least squares minimization problem. It's regression. You just solve for these weights. So that can be very, very fast to optimize for. If you're trying to match biological data, one of the things you can do is when you're randomly generating these weights, you can choose the distribution that you're choosing those weights from in order to give different properties to these neurons here. So if I want a particular amount of sparsity in the activity, or if I want particular maximum firing rates or things like that, all of that, if I have some desire, so even if I'm doing this on hardware and I know my hardware only supports like, I don't know, 100 spikes a second, or it wants to be an average of 10 hertz or something, then I'll often just sort of do that just by randomly generating these weights, but then randomly generating these weights from a distribution that'll cause that to happen. But then also, and then you optimize least squares minimization to optimize for these weights. But I'm not limited to that approach. If you like backprop or you like other sorts of methods, cool, whatever you want. All right, so far this is like, all right, fine. This is just normal neural networks. I'm just doing a really small version and throwing out backprop. That seems weird. What can I do with that? Well, if my claim is that this is going to be my minimal component that I'm going to build up neural networks with, and arguably this even a big neural network that's like trained with backprop or something, you could break down into components like this, right? So if we could understand what this component is good at approximating, then that would tell us what our sort of basic component is that we have to break algorithms down into in order to then build neural networks for each part and then build things back up and give ourselves a big giant neural network that does what we want. So we want to understand a little bit about what this particular simple minimal neural network can be good at approximating. Well, okay, that's going to depend on the neuron model. It's going to depend on the encoder weights. It's going to depend on the decoder weights. Fine. As a particular sort of simplest case, that's actually still pretty generic, and like almost anything that you do with a single layer neural network, no matter how you configure it, the things I'm about to say are going to be true. But the particular example I'm showing here is leaky integrated fire neurons, randomly generated E values such that the neuron properties across some range of inputs. So what I'm plotting here is a range of inputs. I've got a one-dimensional input in this case, so I've only got one input value here, and then a set of weights. And I've just set those weights and the biases on those neurons to give me tuning curves that have some, maximum firing rate, and some, the biases are set so that, at least the neurons turn on at some point in this range. Right? But that's just setting the gains and biases from a random distribution. Okay, so fine, if we fixed this side of things, and then the output is a weighted sum of those, well then, if I wanted to characterize what's the set of things that I could build by taking these tuning curves, these individual neuron responses, and do weighted sums of those to produce an output, if I wanted to characterize what those outputs can be, is there math that would tell me what this particular set of curves would be good at building? And depending on what courses you've taken, you may recognize this problem. This is an overcomplete basis space, right? This is, hey, I have a bunch of components that I'm going to do weighted sums of. It's an overcomplete basis. If I want to understand what that basis space is, I do singular value decomposition on this data, and it tells me the set of functions this simple one-layer neural network is going to be good at. Okay. So you do piece, and again, you can do this on whatever neuron models you feel like, with whatever distributions. Pretty much anything ends up with the graph that I'm showing here. This is the set of functions that this set of neurons is good at approximating. So by changing these weights here, I can have this set of neurons compute any of these functions. And if I wanted combinations of these functions, then again, that's also fine. I can just sort of do weighted sums between these functions. Okay. If these curves look vaguely familiar to you, these are shifted versions of the Legendre polynomials. So what this is, so another way to say this, so another way to interpret everything that I'm saying here, is if you have a single hidden layer neural network with reasonable sort of neuron properties, I can tell you the class of functions that you're good at, that group of networks is good at approximating. And it is literally the polynomials, and the higher the degree of polynomial, the worse you get. So another way to say that is, hey, if I have some function that I have neurons approximating, and I want to know what they're going to end up doing, then I could take that function, whatever it is, I could do a Taylor series expansion of it, truncate it at a certain point, and say, okay, that's probably about what my neurons are going to do. Okay. Another way of saying that is one hidden layer group of neurons is really good at approximating smooth functions. Okay. That all makes some sense. That's sort of a core concept that I want to make sure people are vaguely comfortable with before going on. Do we have questions? Are we happy with that?
No, sorry.
I have a question. So what do you do PCA on? I don't get it.
Yeah, literally this data. So we just do PCA on this data here. So this is a matrix that is number of neurons by my number of sample points. Right. So I'm just doing that. Yeah, so this is just trying to do that of a yeah, and you can do that for any data you want, or for any neuron type you want. Okay. All right. So my point out of that is, and Michael, feel free to fill in details and whatnot after, but my point out of all of that is that at least tells me that if I'm going to break a big giant algorithm down into components, if I break it into components that are functions that are smooth, so functions that are well approximated by low degree polynomials, then that's going to let me, I know that I'll be able to train neural networks to approximate those functions. And then I can staple things together and build up big algorithms. So let's go and take a quick look at what that looks like. It's like, okay, fine. I can I have some X value, X is a vector. I'm feeding it into some neurons. I can get out some value Y. And if I'm using just a single hidden layer, cool. All right, then I know this has to be a smooth function. If I have some much more complicated function that I don't know how to break down into smaller things, cool, do a multi-layer neural network in there as well. Everything else is still going to hold. But for the stuff that I'm talking about here, let's just think about breaking it down into single hidden layers. We feed in X and Y, and I'm like, okay, I want to build up a larger system out of that. Well, that's easy. I just take Y and I feed it into another group of neurons, and I compute some other function Z. And that's fine, that's dumb, that's simple. But then I've got an interesting problem. In fact, we ran into exactly this problem implementing this algorithm on Luigi. Because we're like, well, hold on a second. If I've got neurons A and neurons B, and someone gives me hardware that lets me connect neurons to neurons with connection weight matrices, or if I'm trying to model the brain, which connects neurons to neurons with connection weight matrices, that doesn't look like the diagram I'm just drawing here, right? Like this Y thing doesn't exist in a lot of hardware, and it doesn't exist in the brain. All that maybe exists is direct connections from A to B. So how am I going to deal with this problem? And the way we're going to deal with this problem is to note, well, hold on a second. This is a connection weight matrix. This is the decoders. This is a set of weights, this arrow here. This arrow here is a set of weights, the encoder. And these two sets of weights over here, I built this as one neural network on its own. And I built this as one neural network on its own. So these are like these two sets of weights were built together, fine. And these two sets of weights were built together. But now that I'm connecting things together, I've got this set of weights, and I've got this set of weights, and I've got this green box, which I already said doesn't have a nonlinearity in it. So that means this is a linear operation, this is a linear operation, this is a linear operation because it's nothing, it's the identity operation. That means I can get rid of it. Right? If I have hardware that only lets me take neurons and connect them to neurons with connection weight matrices, cool. All right, then what I just built, I can just multiply those matrices together and I get the connection weights that are the direct connection across this. Some hardware lets me separate it out. Some hardware lets me keep it separate. Some hardware doesn't. This is a hardware trade-off. Generally, if you have hardware that does it this way, it's nicer because these connection weight matrices are smaller. People might also recognize this as factoring a weight matrix. So it is a somewhat common technique in deep neural networks of after you've done all your training, you take your weight matrices and you try factoring them out into smaller weight matrices. But we're sort of doing it the other way around. We're just like, we're building it knowing that these are sort of components to be factored out. Okay, that's a little bit weird, but at least fine, we can go ahead and composite things. And then that means that I could then build up big giant, if I have some algorithm that I want to implement in neurons, and I can break it down into these components, well, cool, all right, I just go ahead and define these components like it's a function, like it's a programming language with functions being computed all over the place. And then you just sort of place everything together here, train up all those individual networks, and then merge all those weight matrices together, and then you get your actual weight matrices that would sort of do all this. Okay, fine, but so far I've only talked about feed-forward stuff. And I haven't talked about time at all. And this is where we're going to get, so far I don't want you to be impressed. So far what I've just shown here is, okay, yeah, fine, I could break up, train a bunch of small networks and staple them together, yay. There's going to be one more step that is going to give us an extra capability on top of what I just described. That's going to be really important. In order to do that, I've got to pay a little bit of attention to time. So most of the time in biology, and a lot of the times in neuromorphic hardware, depending on what sort of hardware you're looking at, when you connect between neurons, there is some sort of something in time is happening. Sometimes it's just a one-time step delay. You know, it takes one time step for information to go from one to something else. In biology, a lot of the time, it's a low-pass filter. If there's a spike coming out of one component, the actual input into the next component is this postsynaptic current. So this is the plot of sort of current. So there's a spike that happens at this point in time here. And then this would be the actual current that flows into the next neuron. And you can sort of see that as a low-pass filter, or as a, here's the impulse response. I will note that we often think about this sort of synapse dynamics only in the case of spiking neurons. There's no reason to only think of it in the case of spiking neurons. We can also do it for non-spiking neurons. And it's the same math in both cases. It's still just a low-pass filter. Okay, or it could also be something else. But the most common synapse model is a low-pass filter. If we stick with a low-pass filter, the math is going to be a little bit nicer. But again, if you want to do a more complex synapse, it just complicates the math that I'm going to show on the next page a little bit. But there is some temporal dynamics being imposed here. So let's be explicit about that. Let's write down what the hell that is. Especially since, well, hold on a second, that synapse, that's like, that's applying when we connect from neurons to neurons. But since this is a linear time invariant operation, that also means that when I split that connection weight up into those two linear components, the decoder and the encoder, the fact that that synapse is really sort of technically applied, right here to the output from these neurons, it's linear, so I can move it around. Right, so it's totally safe for me to move that from here to here. I haven't made an approximation, I'm just reorganizing the math. And so that tells me what I'm going to get out of this system. That if I had have trained up this first network to be just y equals a function of x, and then I add on a synaptic filter on this output, okay, on the output from the activity of the neurons, then that's the same as putting a synaptic filter on the output of like the weighted sum of those neurons. And so that means that the actual output I'm going to get can be written as, okay, it's the actual output, what the normal output would be, convolved with this particular function. Okay? If you're not used to convolutions, another way to say this is it's going to be smoothing the data over time. If I do a sudden change in x, that's going to cause a gradual change in y. Okay, it'll still be computing whatever this function is, but I'm going to get a gradually changing version of it. Fine. So what? Okay, so that does mean I'm going to have, okay, so when I'm building this big algorithm up here, I do have to recognize that if I'm passing information between components, I'm going to actually be passing smoothed versions of those things between components. So that's going to change my algorithm a little bit. It's going to introduce timing in my algorithm. More importantly, it's also going to let me express what's going to happen if I do a recurrence in this. So everything I showed so far is all feed forward. What happens if I try taking a component and connecting it back to itself? So if I add a recurrent connection in my neural network, and of course that recurrent connection, just like any of these other connections, would be approximating some function. So, okay, all right. But then can I characterize what the heck this value is going to do over time if I add in this recurrence? Okay, now that I've jumped through all these bizarre hoops, I can at least write this math. And really being able to write this math is why I've gone through all this weird process of setting up, of defining, stapling together neural networks in this way. It's so that I can write down this equation. All right, because this is just simply, all right, this is what will happen, assuming the neural networks are good at approximating these functions, how is y going to change based on what on these functions? And so if I write down that math, okay, what the heck is that going to mean? So fine, and again, and just to be really clear, I've trained up this neural network here to approximate f of x. And then I've trained up this feed-forward neural network to approximate g of y. And then I've trained up those two networks. One of them is approximating f of x, the other one's approximating g of y. They're just two different networks that I've trained up using whatever the heck I feel like. And then I'm going to put them in a situation where I'm adding this synapse and I'm taking this output and feeding it back into the input. Right? So I've trained these things as feed-forward networks, and I'm just going to shove them in as this recurrent monstrosity with temporal dynamics being added into it. And my hope is that I can understand what the heck this resulting component is going to do. All right, well, I can write it in math. Math should let me solve anything. So what should I do in order to try to deal with this math and try to understand what the heck this system is going to do? Well, if I hand that equation to a mathematician, the first thing they're going to do is say that convolution is a horrible, horrible operation, get rid of it. And the common way to get rid of it is by taking the Laplace transform. So I take my equation, I do the Laplace transform. This h of t, the equation for the synaptic filter, so this, this thing here, the equation for that, if you go and look it up, it's one of these standard ones that's in the back of the textbook. It's a low-pass filter. Here is the Laplace transform for it. And then we have the Laplace transform for whatever these functions are. Once it's in this form, now I can do algebra on it. I can rearrange it. And now I'm like, okay, fine, I've done rearranging it. Now I can take it back into the normal time domain. And this will tell me how y will change over time, how this particular group, this neurons, whatever this group of neurons is encoding, how will it change over time based on these two functions. And importantly, this function here, that's being controlled by the input connection weights to this recurrent neural network. And this function here literally is the thing that's controlling the recurrent connection weights on this neural network. So that means that if I have some particular differential equation that I want to implement, then I can build that network by training up two feed-forward networks. One of them's approximating this function, one of them's approximating this function, and then I just staple them together in this weird way. And so and then I just generate these connection weights just by combining the weights of these individual trained networks. And then that will guarantee that the resulting system will approximate this differential equation. This is a new capability. This is something that's very, very hard to train with backprop through time. If you want to train up recurrent neural networks, that's just really hard. This gives you sort of an immediate way of solving for connection weights that will do what you want when you connect them recurrently. Okay. So one of the things that we will do maybe is show some examples of building that, but just to sort of highlight what this lets you do. So very simple system. I've got a layer of neurons here on the left. I've got another layer of neurons here on the right. I'm just drawing them as squares, but they're just one layer. And all I have is I have a recurrent set of connection weights on this set, and feed-forward set of connection weights on this set. And now I've got a system where I can say feed in pulses, and I get out from this group of neurons, in this particular case, the integral of what the input is. Okay? And the way I do that is literally by, fine, this is the differential equation I want to approximate. The math on the previous slide said, all right, I train up one feed-forward network that approximates this function. That's really easy. That's literally a neural network whose output is the same as its input. That's an autoencoder. We do that all the time. I can do that with any group of neurons. And this bottom one here is an autoencoder that's just scaled by a constant, so that's also trivial. I just train up those networks with whatever approach I feel like, and then I use the math on that previous page to build up what these connection weights are. And then once I have them as connection weights, I can go run that in any hardware I feel like, because at the end of the day, it's now just neurons and connection weights. And we just go off through all this weird math as a weird way to generate those connection weights in the first place. This, of course, also extends to whatever other things you want, oscillators. I'll also comment that one thing that is really hard to build with traditional techniques is controlled oscillators. I'll be talking more about those next week in the central pattern generator talk. But what this is a group of neurons that will oscillate, but the speed of its oscillation is controlled by another group of neurons. That's something really, really hard, again, to do with backprop, but it's trivial using the technique that I just showed, because you can just write down, okay, here's the math that I want you to implement, solve for it in a feed-forward way, and then take those weights and connect them recurrently. So that is the core idea about neural engineering. If I have some complicated thing that I want to implement, I want to sit down and decide myself what overall calculations I want this overall neural network to do, break it into components. If those components are simple enough that are okay, that are smooth, relatively smooth functions, I know that any component that's small enough to be a smooth function, I know I can get away with just a single hidden layer neural network. If I have a component, I don't know, fine. If I'm building a big system and part of it has a vision component, fine. Nobody knows how to break vision down into smaller functions, so fine. For a vision system, I'll just steal whatever the heck deep neural network someone's already given me. But for the rest of the parts that I know, especially if I'm doing sort of motor control tasks or all sorts of other sort of anything that's an algorithm that I written in terms of with ways that people normally write algorithms, I know how to implement that. And if those algorithms have differential equations in them, I also know how to implement that. And that gives you a pretty huge class of things you can implement, as long as you can break it down into those sorts of components. And then we can also put guarantees on how closely you're approximating those functions. That's one of the other things I really, really like about this, is because I've broken these things into components, I can know how well I'm approximating each of those individual functions. I can start putting bounds on my error of the overall system. I find that really exciting. You get to sort of design things at this level, and then you go through the steps that I just showed of okay, we break that into single hidden layer neural networks, train up those hidden layer neural networks, single hidden layer neural networks, however you feel like, and then get rid, you initially have all these intermediate variables, and then you can get rid of them. And now you are left with just a layer of neurons connected to a layer of neurons, connected to a layer of neurons, connected to a layer of neurons, it's connected to itself, and I just have some inputs and outputs. And then that lets me put these sorts of things on pretty much any hardware that's out there. Cool. All right, so yeah, we want to express models in terms of vectors, functions, differential equations. Choose whatever neuron model you happen to have in your hardware or whatever level of detail you want. Half the time I just use rectified linear units, but then if I'm comparing to biological data, cool, I'll switch over to spiking neurons. It's a fairly fast process because each of those individual components is fast to optimize on its own. When you switch neuron models, yes, it's going to find different weights, but that's fine. But then once you've generated, you can then go ahead and evaluate performance and compare data. The main thing that is going to happen is you do want to make sure that the functions you're implementing are smooth. If I try implementing this function here, sort of an if statement, if x is greater than 0, output a 1, otherwise output a -1. If you try implementing a function like that, then you're actually going to end up getting a function like this. And maybe that's okay in your application, If you really, really want this really sharp change, fine, you're going to need to add more neurons, but that's fine. And then, of course, yeah, using different, and then the same restriction is there for differential equations. You want smooth differential equations. So that's cool. That's awesome. Lets you implement lots of things. One caveat I will put in there is that if you're not used to working with differential equations, programming with differential equations is hard. You don't have for loops. There's no if statements. Things don't change instantly. I can't just like on one time step be doing one thing and another time step doing another thing. So it does force you to think about programming in a very different way. But you know, having this sort of smoothness in both in function and in time. But that's been the approach that we've been using to build up all sorts of things. I mean, Nicole showed the giant SLAM model all being implemented this way. But yeah, we've scaled this up pretty far. In probably another tutorial, I will point out we have software for doing this. And all the stuff I just described there, you can go implement it in any system that you feel like. We have software that sort of does these sorts of things quickly for you. It's a Python package. I can do a tutorial specifically on it as well. But yeah, we sort of just have a system that'll go ahead and do that. At least shows you the diagrams and lets you interact with things. And it's all Python, so you can all like connect to robots and stuff, like, you know, so your IO can be pretty straightforward. But yeah, so we have tools for helping that. Once you have those things, again, they're just made for generating the weights. So if you want to take those weights and put them on some other hardware, cool. We have some exporting things for that right now. We have connections to Luihi and connections to Spinnaker, or just run it on your GPU. Those components all work pretty well. It's an open source package. It has been released in GPL v2, and we're just starting to build up a community to sort of do community development on it. And I'm going to leave it there and give a little bit of time for questions.
So one point building up the community, we do have a channel on the Open Neuromorphic Discord. It's a little under-attended right now from our end, just because we're still building up the community. But if that's a place to reach out if you're interested in finding us, and then also the Nengo forums those are still operational.
Yeah,
right?
yeah, they're still live. I don't know how much longer they will be, but yeah. If there's questions being asked, you're probably going to have to come up to the microphone. I can't hear anything.
Oh, sorry. Seems like everyone is just so overawed by the wonder of the neural engineering framework. There's still for Marcos. You got a question?
Probably that's a dumb question. I guess I kind of. Yeah, so for doing this sort of neuroengineering process, so in order to get in order to do it like this, it needs to be in a differentiable form, correct?
So you need to have an algorithm that you want to implement, and that algorithm must be expressed in terms of vectors, functions, and differential equations.
So either of those.
All of those. Yeah, so vectors, functions, and differential equations. If your algorithm is completely expressible that way, then we can always use these techniques to convert it into neurons. And then the accuracy of that conversion is going to be dependent on how smooth these functions are.
All right. I think that makes sense.
Yeah. So yeah, it can be challenging to put it in that form. And there are functions that people are used to using that are surprisingly non-smooth. So like if you have 10 numbers and you want to figure out which one of those 10 numbers is the biggest, That's a horribly non-smooth function. So computing an argmax is horribly non-smooth. So there are definitely some functions that we're used to using as programmers that turn out to be really hard for neurons to approximate. So that tends to be where the problems come up. Because we're like, oh shoot, here's a thing that is trivially easy for a normal digital computer to do, really hard for neurons to do, and often really hard for neuromorphic hardware to do. So that's where the difficulties lie. But as long as you can get it in this form, we can at least approximate it and put bounds on the accuracy of that approximation.
I have a question, Terry. Why does the neural engineering framework only do rate-coded models?
That is a much longer question, and I would say it doesn't. So all of the stuff I just described there works fine with rate neurons, works fine with spiking neurons. The only constraint I'm trying to do is that I do want your neuron models to be time invariant. If your neuron model itself changes over time, that's a bit of a problem, and I don't think anyone wants that anyway. Fine to have the weights change. I don't care if the weights change over time. So we can do any sort of learning that you want. If you want to do learning on top of what I just described here, cool. Either online or backprop. Some people have used what I've just described here as just a really weird way of initializing networks and then throw backprop across the top of it. That's totally fine. A lot of the times what we do is we'll use this to build an initial version of a network. And then if we're doing, say, adaptive control, where it needs to learn sort of, oh, hold on a second, my motors aren't quite how I thought they were, we just treat that as doing online learning on the weights while we're doing this. So the only constraint we have in terms of the neural representation is we are assuming that it's time invariant. But in terms of, is this a spike code or a rate code? It is both. And that's fine. Really, it just depends on what sort or how long a time constant low pass filter you're playing with. And I will note that in different parts of the brain, this time constant is very different. So in some parts of the brain, this is about 2 milliseconds. In other parts of the brain, it's more like 200 milliseconds. So I think there's lots of neat things you can see about how the brain is processing data by looking at the different time scales of this low pass filter. But that's a whole other conversation.
All right. Well, we've got
I have a question here. I'm sorry.
Please go ahead.
Oh, okay. Hi, Terry. Can you go back where you did when you define the neurons? I think I saw that each neuron have to be different, right? There are those curves. So you need neuron variability within each group, right?
So the nice thing is this is actually not variability from the neurons. In this particular case, this is variability from these weights and from the bias value going into each neuron.
Okay.
Yeah. If I do have variability in the neurons themselves, that's also fine. In fact, when we've done analog hardware based on this, we set up the transistor mismatch in order to give decent distributions here. I do need a decent distribution here. But
so you can represent whatever function at the end, right?
Yeah, because if I change this distribution, that's going to change the result of this PCA. That's going to change the class of functions I'm going to be good at approximating. So I really like that when designing hardware. If I'm putting variability in my neuron itself, or if I'm allowing some variability, say in the bias and in the weights coming into the neurons, I can at least figure out what a good amount of variability would be.
Oh, perfect. Thank you, Terry.
Yep.
All right. So we've got 2 minutes until the next talk. So maybe, Terry's available online. So if anyone has any further questions, it's easy to get in touch with him on the Discord or on the WhatsApp. But let's call this session now. Thank Terry again. And move on to the next talk, which is the language and thought talk on
Multonian echo learning, so a way of learning biologically plausible alternative to back propagation through time. But I'm not presenting that, so.
Yeah. Thank you, Terry.
Look. Okay, so I think so. Hi everyone, I'm Guillaume. I'm a PhD student at the University of Groningen, and today I will talk about learning long-range dependencies through time reversal symmetry derecking. And why it's relevant for here is that it's a new algorithm that is much more easy to train on-chip system, and specifically to do time series to time series mapping. So the thing that we are replacing is really back propagation through time. And it's also relevant for the brain. Okay. And so here, just a teaser about the video that I will explain during this talk is here we have a physical system. So it's a bunch of strings and masses. So we can consider the strings as parameters of a machine learning system that we want to learn. So in machine learning, we want to find the gradient of a loss with respect to this. And here I will show how this system can really implement backpropagation through time. So the punchline is here you are seeing a system computing backprops through time. Okay. So the motivation. So we want to do deep learning grounded in physics. So if we put like all the machine learning hardware on a continuum, on one side we have hardware that is very general and that use digital hierarchy. So for instance, here we have GPUs. And so on top of the GPU, you have a bunch of level, digital level where you have CUDA, C++, and then you have your library, PyTorch, you can have transformer on top of it. And so it's a very structured system. And then we can move to a more specialized hardware that are closer to raw physics. So here it's a chip from INI, neuromorphic chip, where you really have physical neurons, so analog neurons that are implemented on the chip. And so you have less of this kind of digital hierarchy. And if you go crazy on the direction of raw physics, you have reservoir computing. So here they do machine learning with a bucket of water. So what you do is you take a signal, for instance, someone saying 1, so a speech signal, you send it via vibration into water, you have a bunch of nonlinear transformation, and then you have a camera that looks at it, and you try to decode and classify the signal. And so there's a lot of people that are trying to go in this direction to try to compute with physics. So they try to do it with vibration, voltages, lasers. And what we are trying to do in this work is to bring deep learning here. So whenever we go toward raw physics, the issue is there's less learning. So here, for instance, it's more chips for inference, and reservoir computing, there's nearly no learning. So we want to train a physical system. So that's the equation for a general physical system. So we have a time series, U. We have parameters, theta, that are represented by these knobs. So steps that we want to change. And F is describing the system, and phi is the state of the system. And so like that, we can describe any physical system. And the thing we want to do is regression. So from this input, we will want to map it to have a mapping to a target. And so here we have a loss, that is time varying. And we are trying to minimize this. So we integrate the loss over time, and the system is obeying this equation. So why it's also relevant for neuroscience? It's here. So this is a quote from a recent paper. So in neuroscience, there's a lot of alternative of backpropagation, but not a lot for backpropagation through time. So here it's a list of algorithms. I guess you know many of them. And but for backpropagation, there's nearly none. So what do we want? So that's the requirement. So we want a system, so a single physical system that is able to do training and inference. So this is what we mean by forward only. So we don't want backpropagation through time, because backpropagation through time because backpropagation through time require two systems, one for the inference and one for the learning. Also, we want to have no access to state Jacobian. So this is, we don't want to use RTRL. So RTRL uses explicit computation of state Jacobian. And at the end, we want a system that is scalable. So for instance, reservoir computing, you don't train all the parameters.
So what is a state Jacobian?
A state Jacobian is, so f is a function that depends on the states, and it's the state Jacobian is a derivative of f with respect to the states.
So what is that state? Like what is it doing?
What do you mean by that?
Like that state, like how does it play in that system?
So when you have a physical system, you just have this, right? You have this that is implemented. But if you want to do backpropagation through time, I will have slides on backpropagation through time. What you need to do the learning is you need to compute the partial derivative of f with respect to phi. And so it's something completely else that is not available on the physical system. And we don't want this. So we want to be able to do training only with this physical system, nothing else. Okay? So what are the different approaches? So we have classical deep learning. So I will present different stacks to do training plus inference. So the first stack is classical deep learning. So you have your model that is in code. Then you write it in PyTorch or JAX. You compile it to machine code. You execute on GPU. And from this whole pipeline, JAX or PyTorch will compute all the gradient you need for learning. Then if you have physical system and you want to do training off chip or off physical system, you have your physical system, you have those inference. Then you have to, I think, yes, then you have to model F. So find the equation of the physical system, code it into your PyTorch or JAX, and then you do the whole thing and you get the gradients. What we want to do is this. We want to use the same physical system for only F for inference and for learning. And the only thing we will allow us is to add a feedback from the loss to the system. Is it clearer? Yes.
What's the feedback? Or are you going to go over it?
Yeah, I will explain how it's parameterized, but intuitively it's just something where you compute the loss at some part.
Yes.
And you will inject it as input to the system. Okay, so that's backpropagation through time. So here are the equations. So if you want to train the system and find the gradient of the loss with respect to the parameter, you need to run this discrete time system. And that's here where, and there is an analog in continuous time. But that's here that, if you look at this equation, I will not go too much into details, but there is this. And this is like the gradient, the partial derivative of f with respect to phi. And it's something different from here. So if you want to implement this in hardware, you need another system than this one.
Yeah. What is phi minus k plus 1? Like, what is this phi minus?
It's just the time index of.
But wouldn't it be phi k?
No, I think. Okay, yeah, I will explain it later. But we have like in this work, we do strange notations.
Yes, minus.
In which like the system is parameterized from -t to 0, so inference. And then learning is from 0 to t.
Okay.
And so then that's where I'm coming. So here you have to run this, and you have to evaluate the Jacobian at the state of the trajectory of inference, so between -t and 0. So it's one of these that you have like minus term. And that comes to my second point. When you do BPTT, you need both the Jacobian of the system And then you need also the memory of the trajectory you did during inference. So that's really why backpropagation through time is really hard to do in hardware, because it's a computation that is very different from the inference.
And what is lambda now? The loss? No.
Lambda is the state. Yeah, it's the state of the backpropagation algorithm. You know, like you can think of backpropagation through time as a discrete time.
Where you go kind of one
Yeah.
time step at a time forward.
Yes.
Okay. got it.
Yes. So here,
Like lambda 0 is spatial backprop.
yeah,
Time
and this
zero.
one is, if you want the formula, it's like the partial derivative of the loss with respect to the states at the given time.
Okay.
It's propagating the gradient of the loss backward.
Right, all the way up to time step k plus 1.
Yeah,
Or
capital
minus
K. Yeah,
Okay.
yeah.
Those lambdas are used to update the thetas, the parameters.
Yeah, so and then once you get, so your backpropagation through time is you run this system, and then you have a way from this lambda to get the learning that is now available to change your theta. Okay, so if we come back to what we wanted, forward only, so a single system, no access to state Jacobian, and scalable. Deep learning is really scalable. So it's running very fast on GPU. But you need to have access to state Jacobian and you need two systems. So yeah. The brain, you could claim that somehow it's able to do the three because it's a single system. You don't have like separate system between an inference and the learning part. It's hard to see how it could compute state Jacobian, and it's scalable in the sense that it seems like it works well. And so zero order method, I did not go too much about it. So people, when they want to train this kind of system, what they do is they will perturb one by one the parameters of the system and look how it changes loss. And it's not scalable because when you have a huge amount of parameters, like in a big transformer or a big system, you will have to run the system proportional to the number of parameters you have. And so that's really not so scalable. And that's where deep learning is really shining. Like you do one computation, you run once backpropagation through time, and you get the gradient for every parameters. Yes. So the proposal of the algorithm that I will present is in a specific case. So we will assume something about f. And these are the assumptions. So f has to correspond to a Hamiltonian system, and it has to be reversible. Then we can really do what I said, like inference and training with the same system. So now I will explain the two. So that came in when we submitted the paper at NeurIPS with Maxence at DeepMind. And the algorithm is called RHEL, Recurrent Hamiltonian Eco-Learning. So Hamiltonian system. So I will show example and then I will go into the math. So a Hamiltonian system, if you put the mass, the string, and you see that the system, if you launch it, it will oscillate. This is a Hamiltonian system. And these are second order differential equation usually. And in all the talk, we will parameterize their state like that, where we have capital phi that is a full state, and it's composed of the position. So here we see the position. And pi is the momentum. So it's just an arrow that will point at the speed of this mass times its mass. Then we can also couple them together. So we want to move toward machine learning. So we want network of stuff. And here I show just that if you put network of this mass and strings, and then you connect it with an input. So you have an input that pushes the first mass, and all the other masses are connected via this coupling. This is still a Hamiltonian.
Sorry, where is the first mass here?
So here, every pi is something like that.
Right.
And so here you can think of every like that, and just you have to add a force on the first mass where you put the input of your system.
You cannot have any damping, correct?
No. So we are now trying to extend it to damping, but the reversible part says, yeah, no damping.
Conservative systems.
Yeah.
They conserve energy.
Yes. Yes. So that's the way you have general characterization of any Hamiltonian system. So you build your phi uppercase as usual. You have a vector of position, a vector of momentum, and then you build a first order differential equation like that. So you put this J matrix, and you take the gradient of a Hamiltonian function with respect to the state. So a Hamiltonian function, it's just like energy function. So if you know about Hopfield network or a Boltzmann machine, they always use an energy function. And mathematically, it's just a scalar function. So it's a function that takes all this as inputs to the state, the parameters, and the inputs of the system, and output a scalar. So here goes from all this to a scalar. If you take the derivative of h with respect to the state, you have something that has the same shape as the state. So you can then multiply it by j, and you get this differential equation.
And this means the Boltzmann machine would be covered by this.
This means you can plug the energy of the Boltzmann machine like that. Here, yeah, you can do this.
And the states can be the neurons in the Boltzmann machine. And
sorry, you can plug the energy of the Boltzmann machine. You will get something, but not the Boltzmann machine, because the Boltzmann machines don't have this, for instance. You have stochastic system, so yeah, it's really different.
Okay.
Yeah. And even if you put the so now if you go to a discrete system, you can put the energy of the Hopfield network, but because you have this J matrix, you will have something else from the Hopfield network.
And what is the J? Can you explain again what the J matrix does?
J, so you have this has the same size as phi, right?
Yeah.
So you have it's as if you have a position component and a momentum component, and what it does is it sends the position to the momentum and the momentum to the position.
Oh, okay, and then uses that to update the state. Right?
Yeah, and uses that to be the right hand term of this. And yeah, so it's just the constraint. Otherwise, the math does not work. But just there's a lot of systems that satisfy this. In fact, you can rewrite a lot of physics only with Hamiltonian, except for friction. But yeah.
So this is just the equation for, in general, defining Hamiltonian systems.
Yeah, you plug whatever h you want.
And is it always two, like position and momentum, or can there be position, momentum, and like second order something?
So it's position and momentum, but they can be all vectors. So like you have a high-dimensional first order differential equation.
But it's always first order.
Yeah, but you know, like always a second order differential equation, you can recast it as the first order. So first order is.
In fact, the harmonic oscillator does exactly that, right? So
Because
the derivative of velocity equals acceleration, and acceleration is.
I have the example of the harmonic oscillator. I think okay. I go. So let's do a simple example on this system. So that's the Hamiltonian. So yeah, so it's just comes from my hat. So phi is position and momentum, and the parameter is the mass of the system and the spin coefficients. And the important things is it's scalar. So when you compute this, you have something scalar. So now let's do this equation to see how it looks like. So we take the gradient of h with respect to phi. So first the position component, then the pi component. And these systems are really simple. If you want the phi, you will get the square that goes down, and you will get this. If you do for the pi, you will get this. And so now we just multiply this by j. Yes. So we have time derivative equal this. I just remove this. We multiply by j, and we get this equation. Okay, so if it's not natural for you still, I can take pi as a function of phi dots and plug it here. So I just do a substitution, and I get this. And this should be familiar. Sum of forces equal ma, m times the position derivative. So yeah, so it works. A lot of physical systems are like that. Is it clear? Some questions?
Yes, you can't have any velocity there, counting without messes it up, right?
If you put, yeah, if you try to put a term and do the computation, it will never work. You will never have something with velocity.
So you mean that if there is something with velocity, then it doesn't work?
If there's any damping. Right?
Yeah, you can find, yeah, I think it's like that. You can't, but even after we will have the issue that we will need something reversible. But already for the Hamiltonian case, you will need to find a term, an additive term that you put here, that then add here like a damping term. Okay. And it's hard. I think there are tricks, like very unconventional tricks, but for us, we don't even care because we need reversibility.
But
Yeah.
doesn't the momentum term include velocity in it? So the phi, is it under the momentum?
Yeah, but the fact that it comes with a square makes then it means that it will be there. So here you have a pi, but when you look here, it only appears as a second derivative. You only have like a pi dot here.
Right. Okay. But you can have like velocity dependent terms, but they have to be in a specific form.
Yes. Here, yes. Here you can put whatever you want. I'm just saying that whatever you choose here, it would be hard to get a pi appearing here.
Oh, I see.
Yes.
So in this context, does Hamiltonian system mean that it conserves energy?
Yeah. So is a property of Hamiltonian system that it conserves energy?
Yeah.
Yes, the H is actually energy being conserved, right?
Yeah, but there are weird tricks that you can put some stuff that are time varying here, like an exponential of t or something like that, that can mess this stuff. So in physics, they always build some kind of Hamiltonian, and you have always you have all the time conservation of energy, but there are weird tricks that you can play here.
I mean, it's kinetic energy plus potential energy.
Yes. Yeah. And we don't, just a point. So here I'm doing a physical example, but we don't care about physical intuition after. It's just the math applies to everything. And that's just for a bigger system. So here you have a Hamiltonian for this full system where everything is connected. And so now you have still kinetic potential, but you have also a kinetic coupling, and you have also a term for the input. And when you derive this, you apply this, and you get a higher dimensional system, and it's also Newton's law, just in higher dimension. So all we did for now was looking at the Hamiltonian part. So we had an F that was generic, and I just need to assume that F is parameterized like that. Again, so now let's go to reversibility. So we have our system like that. We kick-started from an initial condition X. There is still this notation where we start at minus capital T. And an inference with the system, yeah, it's like any neural network that we use. We start from an initial condition, phi pi, we run the system forward, and then we arrive at the end. I will do an example where the loss is only at the end, but after I will show how we can generalize. And so now we have a loss only on the position. So let me explain this. So every the state phi is composed of phi lowercase and pi, and they are all two-dimensional. So the dot is phi, and it has an x and y component. The pi is an arrow, and it also has an x and y component. So initial condition is dot plus arrow. The loss is only on the dot, but yeah, only on position. So this is inference. Reversibility is this nice thing that if you have a Hamiltonian that is like that, so when you apply conjugation on phi, and conjugation is only you take the momentum and you do minus. If you have this property, the system is called reversible. And so how it works is you run the system like that, and at this time you will change. So at the end you will change the sign of the momentum, and so you start from an initial condition that is this one, and you run the system with the same equation, and you will have the great trajectory. You will redo exactly the same steps.
I know that usually.
That's a basic question. Why does like pi have an x and y component? Like I've seen pi versus phi, and you like put the point on that basis. Like what are the two components?
It's just I'm doing an example where they are two-dimensional.
So
But
like
you could,
two-dimensional. But you're
if you're thinking, so it was very abstract. But yeah, if you want to map it to, so it would be two oscillator. And so one component, so phi x would be the position of one of the oscillator, phi y of another oscillator. And for the arrow, also the momentum of one oscillator. Two in this case. Yeah.
So
Yes.
your dynamics are reversible, so you can go back in time effectively.
Yeah.
By flipping that sign. So
Yeah.
in a way, you're doing back propagation to time, but actually rather than going back in time, you're simulating the inverse process.
Yeah, but the cool thing is so you said we are doing back propagations through time. For now we are just running backward the same system as in France.
Yes.
Right? And if you do just this, there's no way of getting a gradient to train a system. So there is an additional thing, because like if you just find the gray curve, you do not gain anything. You have the same information as the blue curve.
But one way or another, you will do.
Yeah. Yes. Yeah, we want to do back propagation through time, so it looks a bit like back propagation through time. And so here comes the crazy title, learning with symmetry breaking. So here we have a symmetry. So we go one way and through time. And so when we change the time from 0 to t, we do the same thing. So we have a symmetry. We will break this symmetry by adding a nudging. So here we will start the red trajectory, also starting from this, but we will, so this is the condition, that we will add the gradient of the loss with respect to the state at the end. So here we measure the loss. So let's say we have a L2. We just take its derivative with respect to the state, to the position, even only the position, add epsilon, and we just add it on the momentum. And so now we have just same points, the arrow is a bit different, and so we break the symmetry like that. And the nice thing is this breaking of symmetry will encode the error gradient that we are looking for. So just to have a geometrical thing, and important, we have the same system that does this and this. So it's way better than backpropagation through time if we want to implement it. So the geometry of it, okay, forget about this. So the geometry of this, if you just measure the difference between the two positions here, you have exactly the gradient of the loss with respect to the initial momentum. So, okay. So it's the initial condition. Usually, if you want to derivate the initial condition with respect to the loss, you really need to do backpropagation through time through the whole trajectory. And here, just based on the blue and the red, you get directly the gradient you are looking for. But yeah.
So for doing that, so we don't that way we're not applying that error back propagation, right?
We don't need. We just need to run the blue and the red.
Explicitly, but effectively.
Yeah, at the end you get the same result as if you had done backpropagation through time, but you only needed to run the system twice because this breaking of symmetry.
So doing it this way is more efficient.
Yeah, if you have a single physical system. Yeah.
And plus you can go back in time normally anyway.
Sorry, what do you mean by that?
I mean, you cannot go back, nobody can go back in time, right? You're effectively you're virtually going back in time, like this.
Yeah, but there's many physical systems that can do this, right? You just have a mass sliding on a plane. You switch the speed of this mass. If there's no friction, it will do back exactly the same thing. So there's many physical systems, including all the stuff that I showed about the harmonic oscillator with the mass and the spring. They can all be reversed to do this trajectory. It's not something magical. Yeah.
In the hopeful network, as you're saying.
Yeah, and hopefully, yeah, we can do the same thing with neural network. Yeah. So here I said about training the initial condition, but in machine learning we want to train the parameter. There is a similar result for training the parameter. It's just not as intuitive in terms of geometry as this one. And also I just mentioned that it was inspired by work in theoretical physics, but we generalized it to do time series, neural network, and many different things. So that's the math. So if you want to have, if you want to have the derivative of a state with respect to the loss, you just have to look at this quantity. So you have the red trajectory and the gray trajectory. You do difference, you multiply by this. Epsilon is just this term. So you want to push the system not too much. And we can prove that in the limit of epsilon going to 0, this gives the gradients of the cost with respect to the state. Now the one that we want is the gradient with respect to parameters. So it's slightly more complicated, but you still only need the phi and the gray trajectory, the red and the gray trajectory, and you need to do the partial derivative of the Hamiltonian with respect to the state. And so the whole trick of the game is to always define the Hamiltonian where this is nice, because this is the learning rule you will apply in your system. And yeah, and then once you have this quantity, you integrate it over time, and we can prove also in the limit of epsilon going to 0, it's the thing that you will use to train your system. Is it clear? Yeah. So
I'm convinced by the explanation. That's clear. Okay.
So note that there is the same thing as deep learning magic. You run only 2 computations, so the blue and the red, and only with these 2 computations, 2 trajectories, you can compute the gradient of theta with respect to the cost, whatever the size of theta. So this sampling method where you have to perturb every weight one after the other, they don't scale. This scale.
And so in the physical intuition, like what would you read off and plug into this equation? Just the position at the final state at time t after the nudging? Because you only need, what you're saying is you only need the red and the gray, right?
Yeah.
And then those you
At
plug
every
into
time
equations?
Yeah.
At every time.
Yeah, you need to integrate over time. So the idea is you have a small surface that compute this at every time step, this at every time step, that integrates everything. And the cool thing is all these things can be computed locally. I will have an example, a concrete example.
So as we're going back in time, you like you keep this and integrate that.
Yeah,
and
you
at
sum it.
the end of the reversal, then you update the parameters.
Yeah. Yeah.
But you don't need, like, your memory doesn't blow up, like you just add stuff, right?
Yeah, you don't have to, you can forget about the blue one when you did the gray one once you did the integration. Yeah, so it's local in time compared to backward propagation. You don't need the memory of the past.
And you're like the memory of your, like, it's constant, right?
The time memory you need?
Yeah, like constant with
time.
Yeah.
Yeah.
So it doesn't matter for long sequences,
Yeah.
short
Yeah.
sequences.
Same cost. Yeah. Yes.
Actually, this is beautiful. I love it. Now, but just one suggestion here. So you're now computing the difference between the red and the gray.
Yeah.
Effectively, it's a final difference approximation to a gradient, right?
It's a finite approximation of the derivative versus to epsilon.
Yes, yes.
Yeah.
You can get a little, so
Yes.
for any given epsilon, can I do a little better?
Yeah.
Or rather than using the gray, to using the opposite with the red.
Yeah.
Right?
We do this. Yeah.
Okay,
Yeah.
yes.
Yeah. So when we scale and we apply it to huge neural network, SSM and stuff like that, we do like plus epsilon, minus epsilon, and we get better estimate of this finite difference. Yeah. And we have a lot of work on dealing with like numerical issues and things like that. So let's go back to our system. First, I want to generalize to time varying outputs. So for now, you had a question? No. So I had a system where the loss was only at the end. What happened if the loss is at every time step? What you have to do is to nudge the system at every time step. So in your differential equation, you have just a term like that will push the system based on the loss.
In the forward? No, in the backward pass.
During the echo pass. Yeah. So the second pass, we call it echo. Yeah, positive time. And so on the red trajectory, instead of perturbing only the initial condition of the red trajectory, you perturb it at every time step.
But then you computed like the loss based on the new trajectory, the red trajectory? Or you have to memorize the loss as it was on the original forward trajectory?
So the math, if you want to do it perfectly, it's based on the first. But with some very small assumption, you can prove you can also do it with the other one. You just have a bigger error, but in practice it works very well. So you don't have to memorize the loss during the first. You can recompute it during the backward.
But then your gradients will be slightly biased.
Yeah, slightly biased. Yeah. For instance, when you want to do parallel scan, this is the input. You want to calculate it beforehand. So we do it based on the first and memorize. So it's
right. Yeah.
Okay. So physically, when you have something like that, so let's say I define my loss only at this harmonic oscillator, this mass and spring. This term just corresponds to connect the mass 4 to something that moves then based on the target signal. So this is what I was saying, like feedback from the loss. So the only thing you need to do, you get your Hamiltonian system, you just add like a small feedback thing that does not change the whole system. And here you will have, based on how the mass is compared to the target, information from the loss will be injected in the system. And and then as we did, you can prove that the information from the loss that is injected in the system allows you to compute the gradient. Okay. I will not go over it, but it's just to say that in practice we can map it really perfectly to backpropagation through time. So in backpropagation through time, we have this lambda, which is the state of backprop through time, and we can really map it perfectly to our echo trajectory at every time step. So we can really say that the system is really doing backpropagation through time. So yeah, in the paper, if you want.
What was ASM again?
Yeah, so it's a continuous adjoint state method. So yeah, so I talked about backpropagation through time because this is what people are used to, but in continuous time there is something else that is called the adjoint state method, and so formally you have to map it to it, the details. So let's go back to this. We will find I will give you the shape of this learning role that we talked about. So we have this system. So that was the Hamiltonian. So we have a kinetic, potential, and the coupling thing. And the learning rule was something like that, right? So you have to take the gradient of the Hamiltonian with respect to the states. And so let's say I want to train this string. Okay, so I have to just take the derivative of the Hamiltonian with respect to K23. And so and then integrate it over time, and I have my learning rule. If I do some math, and I just take the gradient, the derivative of this with respect to this coupling, everything comes in, right? So I don't need to measure everything, only the activity of, like the position of mass 2 and mass 3 will remain. And this is what we have this. So the learning rule is just, you measure the position of mass 3 and mass 2 during the echo phase and during the first phase, and you have your learning rule.
Why is it a square though? If when you take the derivative, you get a linear difference and now, I mean, I missed
You have
all
a
this.
square here.
Yeah,
You take the derivative with respect to k,
so it goes linear.
so you keep the square.
It's just a.
Oh, I see derivative spread to K, yeah.
Yeah.
Okay, right.
Yes.
Right.
Yes.
So what is that? D2 3 times L equals
The result of the loss with respect to the parameter.
derivative of the loss with respect to that spring
To the
constant.
string, yeah.
It's the limit of this integral to infinity.
Yes.
Limit.
To 0.
So to T. Okay.
Yeah.
Yeah.
In practice, we don't do the limit, right? We just put a small epsilon and we run the two trajectory. It's just the proof goes like that.
And you also discretize the integral, right?
Yeah. Oh, well, if you have a continuous system, you just simplify the integrator. Right. Okay, for people in neuroscience, so here we have a local learning rule, right? So to change this, which has like a crazy influence on the whole system, you only need local information. And you will get the gradient with respect to the loss at every time step. So yeah, for me, I find it very cool. The echo path really looks like replay in the brain. See, in the brain, like sometimes you have in a rodent, you can analyze it. They do something in a maze, you have the brain that goes in one direction, and then during sleep, it goes in another direction.
Is that because it's linear system? In the end, this spring mass system is linear, right?
Yeah, it works for nonlinear system.
Okay.
Everything that is a Hamiltonian. I will give example of neural network at the end. The math is super general, just to be intuitive. I use the system, but yeah, works also very well with nonlinear system. We use it with state space model. We use it, for example. If you choose a nice Hamiltonian, also for neuroscience, you get contrastive Hebbian learning rule. So here you get a Hebbian term where you have to just multiply the states of the two neurons that are connecting the synapse during the echo phase and then the first phase. So contrastive Hebbian, like people found this kind of things in Boltzmann machine, and so it appears at different places. But here we really have it for mapping of sequence to sequence, so much more general than what was before. Yes.
I'm kind of lost, but could you tell me about this phrase with well chosen H? Like, does that impose a limitation on what or
doesn't
that
the H come from the system itself? You don't choose the H, it comes from the energy of the system, if it's a mechanical system at least.
Yes. So I said the learning algorithm works for any system that obeys this. So either you start from your system and you see where you can find an H like that. And if you can find an H like that, you're good, you can apply the learning rule. Either when you want to design your system, you start from the H and you see to what dynamics it corresponds.
Okay, so if it was Marcine's cart pole,
yeah,
that's a mechanical system
Yeah.
with masses and so on. It
Yeah.
has a Hamiltonian already, it has an energy,
Yeah.
kinetic and potential
Yeah.
energy.
Yeah.
And if you wanted to use your method to
Yeah.
learn what the length of the pole is, would it be applicable?
Yeah.
If you could learn the length of the pole,
Yes.
because that's just a parameter of this
Yes.
differential equations of the.
Yeah, you
thing.
could use the system itself to learn how to change its length.
No, to learn the length if you don't know it, because that's a privileged parameter.
To learn the length.
Yeah, you stick a new mass on, like the American
Yeah.
flag we stuck on there.
Yeah.
You know, immediately the mass and damping of the system changed.
Yeah.
Through two parameters.
No damping, you have to lubricate the system with no damping.
No, yeah, no. It's just a Hamiltonian.
There's no damping in your system. There's no
Why
friction.
should it?
No damping. You don't have any damping.
We cannot have damping?
Yeah. No damping.
Oh, the energy has to be constant.
Yeah. But you can.
Oh, I
spin your
see. No, it
system.
wouldn't work for the car pole where you're constantly injecting energy through this motor.
No, input is okay. It's just the damping. You need to assume there's no friction.
Okay, well, okay, that's fine.
Yeah, but the thing you could do with this algorithm is learn the gradient of the cost. So you put a cost on your system, whatever you want as a target. And I
I
could
want to
give
learn
you.
the gradient of the cost. I want to be able to balance it no matter how long the pole is.
Okay, but
Yeah, it should learn the length of the pole.
Yeah, so learn to change the length of the pole.
Not change.
No.
Learn the
Like,
length of the pole.
assume the length of the pole is constant,
Yes.
but you don't know that, it's an
Yeah.
unknown.
Yeah.
Or it might change. It might change.
You want to get, but I think this is
Different, maybe it's not appropriate.
Yeah, but you don't- yeah, yes.
So by restricting yourselves, self to systems that obey this property.
Yeah.
What do you lose in terms of expressivity?
It's.
I guess you show an example with.
Yeah, we still have not.
No, it's really not clear for now. And so we tried empirically, we have like state space models that are Hamiltonian that behave as well as the other one.
But you can always, I mean, just take any loss function that you want, right?
Yeah.
And then add the momentum term.
Yeah.
And then by construction, this is a conservative system. It's like then you
As
can.
soon as you add momentum, it has an energy. A Hamiltonian's equivalent, energy and
Yes,
Hamiltonian.
You add
equivalent.
momentum, but you don't add any friction, just momentum.
Oh, yeah.
Did you add momentum in the plus?
In fact, isn't that what people do with
Adam?
Monte Carlo, Hamiltonian Monte Carlo, right? They add momentum to their loss function, and then the system, this random loop walking system, will explore state space more uniformly and get better learning properties. Well, maybe I'm thinking too far.
So here on the loss, I do not assume anything. You can define it on the momentum.
No,
because
yes. So
whatever.
typically the Hamiltonians are, there is a potential energy and then there is a kinetic energy.
Yeah.
So the potential energy can be whatever loss function you define.
No. So here the loss is outside of the Hamiltonian. The loss is defined only to
Sorry,
do nudging.
when I said loss, I just meant take any function, right? Any function of the parameters or of the system.
Yeah.
And then add a momentum term to it, basically. Right? You have now another parameter which is velocity.
Yeah.
And add that other term, which is the square of that velocity over some mass.
Yeah.
And so now that system you can preserve it, and then you can. Right.
So yeah, you can do many things, but in terms of expressivity, to come back what you said, we have like universal approximation theorem for the system. So, yeah. Maybe you will need more neurons compared to a dissipated system.
But universal approximator
Yeah.
terms are always, you need an infinite number of neurons, so let's
Yeah.
a few more.
Yeah, but in practice it matters, right? Because you have to do everything. Okay. So let's do a quick demo. So we will have only two oscillators. So 1 and 2. The position are represented here. And this is the target.
What is that target?
The target is, so it will move according to a sine wave. So in a sense, you are trying to make this physical system follow the target.
Yeah, what I didn't understand in your video, why is that thing up on this table? Why is it on these legs? Yeah, I'm just curious. No, does that mean something that it's up on this platform?
It's just for visualization, because if it's here hidden behind this, you cannot see.
Oh, I see.
Because you want to map this, you want to make phi2 equal to phi3. So here it's easier to see. For instance, here the target says I want to be in this direction, but this guy is in the other
But
direction.
how is that yellow thing pushing on the blue thing?
It's just a target. So
Yeah, but now it's not connected.
Oh, it's not.
Then afterwards, you will show you that it connects.
yeah, so here I'll just say the target, I will display it here.
Okay.
This will be an oscillation. I will put a sine wave here. And then I will want this physical system. I launch it, and I want the oscillation of this to map the oscillation to be the same.
How are they connected? That's what I don't understand from this picture. How are those things connected together
if we-
mechanically?
Yeah, but if we think of the
Maybe you
machine,
need to play the video, yeah.
Yeah, at the video, you will see that you will put another spring between the
It's
two.
another spring there, okay. That's
Yes.
that's what I'm confused about.
Yeah.
but for the machine learning problem, you don't need to connect it. The machine learning problem is just saying, I will run this system, and I want the oscillation of this one to be the same as this one. And here it's just for display. Right?
Or you're gonna learn the parameters to make them the
So
same.
to make them the same.
Okay.
But then my learning algorithm, in order to work, will have to connect this to this.
Okay.
So no inputs, just a system moving, and we want to change the parameter. It can be mass or spring or whatever, so that this one oscillates exactly like this one.
So, and how are you defining that Hamiltonian for this, like the H value that you just got, right?
It's the same. It's a harmonic oscillator, just like above, it's a slide that
The kinetic and potential energy of that spring mass system,
Yeah.
right?
So here it was for a 6-dimensional system. You just cut and you do two of them. And this is the Hamiltonian.
Is it clear, Marcus? For the spring mass system, you just write the potential and kinetic energy of those masses, add them together, and that's the Hamiltonian. Not this thing, the other one.
Yeah.
Yeah.
Okay.
You just, the momentum of the square, mv squared over 2 plus the spring energy.
For like physicists, they have many ways of finding all these things for every physical system. And once you have this, just to recap, once you have like this Hamiltonian that I just showed, you plug it here, and you get the equation.
Oh, okay, I get it.
So no inputs, output target is this. So we want this to be equal to this. So we just have an N2 loss between the two that we figure out over time. And we want to get the gradient of this guy. Yes. Then we saw that the way the learning work is we run the first phase, which is the inference. So it was the blue trajectory. And then after we run the red phase, which was with a nudging. And the nudging here maps to putting a spring between this mass and this mass. And there is a very nice physical interpretation of this. It means that during this red phase, the nudge phase, so you have to put a spring that has exactly the natural length of the equilibrium of phi2 and phi3. And so here they are like that. So this guy is compressed. And what it tells the system, what it sends as information into the system is you should be toward here because I'm like that. So you will put the system to like information to push the system toward where you want, but just a little bit. So this string is very the coefficient is very small. Yeah.
And now the target system still keeps its same sine wave, and then only mass 2 is modified in its dynamics.
Yeah, but mass 2 is connected to everything. So like information from the laws will propagate everywhere.
Yeah. But so
the target is forced.
The target is forced to stick to the original sine wave.
It's not affected by the other system.
It's not affected.
Yeah, no, okay. This is the target. And so during inference, you don't have
any
target.
Thing that's activating it.
Yeah. And then during the backward, you just play the sine wave backward.
Yeah.
Compared to the.
And this is the moment. No. Where do you do the momentum flip?
So you do an inference. So we run the system forward without disconnection.
Yeah.
Then we have a bunch of oscillation. At the end of the time series, we flip the momentum of this and this, and we connect the spring.
How do you do that physically? What does that mean?
Oh, okay. Other questions. So so it's physical system dependence, how you build this mechanism.
Right.
So I'm trying to build a mechanical system that can do this.
Of course you are.
Just the plan for now. But like if you want to be very stupid about it, it will be complicated. So you need like to have a camera that tracks the position of this and this, and at times t. So if this guy goes in this direction, just put a wall or something that will make a shock and that will change the speed to the other direction. And you have to do this for here and here.
Okay.
A non-absorbing wall.
And then you have to move it back. Right? So you have to move it and move it back. But then for every physical system, you have different mechanisms.
Yeah.
And people in optics, for instance, they found that just putting a mirror does the momentum flip. And for neuroscience, we have to think about it. I guess that will be one of the projects.
Mirror neurons, yes.
I'm not sure the analogy works, but yeah.
And the time is almost over, right?
Yeah. So let's just
for this slot.
Yeah. So we just have this learning rule. So it's the same as before. We just to train this, we measure the position of this and the position of this. We do the difference during the first phase and the second phase. And we integrate over time. So here will be the video. So here I will show the position of this, this, and this. And here I will show the learning quantity evaluated during the two phases. So in France, it's not connected. And then there will be, once we reach here, there will be a flip of speed of this, and we will connect this to here and make the sine wave go backward. So we reverse the time of the sine wave.
With a very weak spin, right?
With a very weak spin. So what you will see is the position that you have here when you go backward are very close to the original one because it's a weak change, but they are not so the same. And here on the learning quantity, when you integrate the difference between the one of the forward and the one of the backward, you have the learning rule. So the difference, the area between the two curves will give you the learning rule. So here you have the change, and you see slight differences. And these slight differences at this part, so the blue area, they encode, if you integrate them, you get the gradients of the cost with respect to the parameter. So this system compute back from through time.
Okay, so I think we're unfortunately at time already.
Yeah,
but we can have a separate session to continue because I would like to see the state space model stuff.
Yeah, no worries, we can go back in time. Just
yeah. Wow. Thank you so much.
Exactly.
That was awesome.
You'll be posting some code in the.
Yeah.
So we can make like, so we could play with this.
Yeah. We put a code where you plug your Hamiltonian. So you have a system in mind, you find an Hamiltonian, you plug it, and you can do everything.
That's so good. I do have to ask, like the mathematics that you presented is impressive. What does the code look like?
You asked that with fear.
Yes.
No, it's super simple. Like you create a model.
Yeah. So you just like write differentiate. So you just write the Hamiltonian and do auto differentiation.
Yeah. So you can even be super simple like that. You put the Hamiltonian, you use JAX, and from this you can like define the dynamic because it's just gradient of the Hamiltonian with respect to the state. The learning rule is gradient of Hamiltonian with respect to parameter. The code is super simple. And I even write a custom automatic differentiation. And then when you call grad on JAX, it does this in the background. So
is the notebook already in the channel?
No, it's
okay. I mean, fair enough. You have to work on the fly.
Yeah, and just like everything works at a higher scale, we build it with state space model. But I think the cool next step would be to find a physical system that maps to a hardware. So either a spiking chip or whatever. And really work on how to do this on chip on real hardware. Yeah.
Wow.
Thanks.
It's like the very early stage basic idea for what we could do with the Maverik accelerator. We're not sure yet whether it makes sense or not. But we figured yesterday, just talking, that it may be a good idea to apply graph convolutional neural networks for Maverik, since it helps to address the bottlenecks of the architecture. As far as I understand for now, what would be the bottleneck? It would be too many accesses to the memory for the cores, right? And also the fact that we generate more than one data at the output of each core. But we cannot take a scene for each clock cycle by the processor. So we would like to, ideally, we would do multiple multiplications and only then output something back to the processor, right? So I will go back to the Maverik, but for now I will focus on graph neural networks. I don't know how many of you are familiar with the basics of it. I am not. I don't have much knowledge about graph networks, except of one very particular method for graph convolution networks, which is usually considered very well for hardware implementations because it's fairly efficient in terms of memory usage. So I will focus on that. And I will focus on the context of event-based vision, even though it doesn't have to be that. But this is what I work with, and this is something quite easy to understand the context of graph convolutional networks. So to have graph convolutional network, we have to first have some kind of the data that can be represented with a graph. For event vision, it's fairly simple because each event can be represented as a vertex in a graph, and then we can define edges that connect events and define some kind of local relationship between events. For example, we can connect events which are close to each other in 3 dimensions, which is x, y, and time. So if they are close to each other, they are connected, and the connection defines some kind of local relationship between them. All right. It's fairly common right now. There's a lot of work about that. And with representations like that, like hides the bar. All right. This is like actual graph from some event data from one of the data sets. When we have a graph representation, we can feed it to the graph network where we perform graph convolution. Traditional convolution on 2-dimensional matrix-like representations is just, well, you're familiar with it. For graph neural networks, convolution is performed on vertices and all vertices connected to it by edge. Okay,
Yeah.
I've got to that.
Near the neighbor or extended?
What do you mean?
Only direct. Only direct connection.
Only direct connection, yes.
Yeah, that's good.
Yeah, I will like walk you through the kind of pipeline of graph neural networks for event vision, especially in the context of hardware. Because first we have to create a graph representation, and throughout this entire presentation, I will assume that's what we want to achieve is at least to some extent action-enabled processing of events. So we don't want to aggregate all the events, then create a graph, and then feed it to the network. We would like to perform computations on the events as soon as they are fitted to our system from the camera. Okay, so to do that, usually we first normalize the values of events to some nice uniform values. In our work, we create usually graphs which can be represented like some kind of sparse 3-dimensional matrix representation. You understand that? So the size of the data would be in the entire graph would be 128, 128, 128 in 3 dimensions, x, y, and time. We can do any other value, just an example. So for each new incoming event, we want to use it to update the graph. First, we normalize it. So we normalize x and y values from 0 to the resolution to the values we set for our graph representation. And for timing, the timestamp, we also define some time window, which is the amount of data we need to produce a single prediction, enough of data so that we can analyze it in a sensible way, and we normalize it in the same way to the same shape. We don't have to do that. You can have different shapes in each direction, but just for the sake of the example. All right. Then usually we put it doesn't really matter. The second thing we have to do is we have to, with this new event, update our graph representation. We do a couple of assumptions here that are not necessary, but perfect for hardware. We are not the only ones who do that. It is fairly common in the literature. We can create a directed graph with time. The idea is that we don't want the new event to force us to update already processed data, already generated graph. What we want is that for new events, we just add it to the representation, and we don't have to change in any of the computation that was already happening. And we can do that with graph directed with time, which just means that each new event is connected only to already processed ones, and the connectors are directed. So the already processed events don't update their edge list, right? Cool. Well, we can do that anyhow. We just have to, for the new event, check its neighborhood within some radius we defined for the edges. Find all the events that pass our half sphere condition, so they are close enough to be connected. and you connect them in this method, all right?
How do you actually store the events? Like you store the X, Y, and time component of each event, or do you only store the graph object that you will compute on?
Well, it depends on the stage of the network. For graph generation, I actually have a hardware module for it, so we could use it potentially. And we do that with the memory of the X times Y size. So we encode all possible events, and we just store information for each place when, in what time step we last recorded event for this particular place. In this way, for each new event, we just we just make like 29 reads for radius of 3, but we look through the context and we find out all the events that were in a particular X and Y space at any time, and we verify the timestamp we had in this memory, whether it's close enough in the time direction.
But this is not storing the connections between the events yet. So you have one structure where you're just storing all of the recent events that you had. You truncate the X and Y coordinate, or you like round it.
This particular memory I use only to define connections.
Yeah.
But the actual events in my implementation, for example, just needs the X, Y, T information and the list of all the edges with the related information. So we have an edge at -1, -1, -3 in the time dimension, for example. Right?
How do you store the edges? Do you store in adjacency matrix, or do you have some very specific structure for storing this directed graph?
I don't. Well, I can answer that, but it doesn't really have any meaning in the context of your accelerator. In the first part of my implementation, I process data completely asynchronously, so event by event. So I don't store it in any memory. We just put it to the first convolution layer, just the X, Y, T, and list of edges information. Right? Anyway, what we work with, we can change that, is a radius of 3 in each direction, X, Y, and time, which gets us to a maximum of 29 edges for each vertex. It is only 21 because we have additional assumption that for each particular X and Y, we can have only one neighbor. So we can imagine that we have a new event here, and here there was an event in T-1, but also some event in T-2, right? But when we look for the connections, for the edges, we just find this one and don't look for any other previous one. This is why in the previous slide we can only store the timestamp of the last event that occurred for a particular space.
But so that is that robust?
Well, it works fine, and that's fairly. We are not only people who made that assumption.
No, I'm just getting.
Yeah, the accuracies are great. Anyway. All right, so we have this sparse grid-like structure. This is our graph. We don't have to have entire graph to start processing. I will get to the convolution in next slides. We have one edge for particular X and Y. And that's it for the graph representation. So if you have any questions, you don't understand something, I'm speaking too fast. This is a perfect moment.
Why the last sentence? So one edge, one particular X and Y. Why is it exactly one edge?
This is the same thing I said like a second ago. For the same X and Y, we only we don't define more than one connections, just the new event.
Yeah, but but you could have multiple neighbors that you're connected to, like different X and Y coordinates.
Yeah, we can have up to 29 of them.
Okay, so
but not more than one for particular X and Y related to our new events. All right.
So do you take like degree of connectivity based on those events? What do you do? What type of data does it go out? Like for the graph, you say like you only take the next one.
This is basically what I do. This is a part of a big memory with the resolution of 128, 128, right? I got a new event. This it's here. It's x3, y x4, y4, right? So what I do is I look for all possible places where our neighbor, so vertex I want to connect with an edge can be. This is based on the radius r in x and y dimensions. But for each particular place, I only connect with the most recent previous event.
If it is less than 3 time steps.
Yes.
Yeah.
Cool.
Yep.
All right. Then there is a graph convolution, which is the reason why I think this is a good thing for our accelerator. So I would like to focus on that. A graph convolution is fairly simple, especially the point net convolution, which is the one I'm using in my work, which is very often used for hardware accelerations. And I would propose to use in this case. The idea is that each vertex, each event has some feature. Okay, we are getting to one more dimension, kind of. Okay, so each vertex has a feature vector, so some kind of values, and edges are not like labeled; they have no value at all. Okay, edges just connect events. So for each vertex, we perform convolution on. We apply the feature vector of this particular vertex to some linear layer, and then we apply the same linear layer for the feature vector of each vertex connected to the currently processed one with an edge. Okay, so we first process my own feature with the linear layer, then I process features of each connected neighbor through the same linear layer. We get a couple of outputs vectors, and I perform element-wise maximum operation on all of them, and I get just one feature vector, which is the input feature vector for this vertex for the next convolution. Right? You all understand that? So for each event, we need up to 29 vector matrix multiplications because we apply the same linear layer over and over again for ourselves and for each of our neighbors. And this is why I think the actual architecture of the Maverik enables us to limit the amounts of accessing the memory, since we can, process the same, use the same layer to process multiple data and get the output only after all the multiplications are finished for all the possible connected vertices. Yes?
This linear layer, how many of them are there? Is it one for the entire cube of graph, or is it one for?
No, this is a graph convolutional layer. So we have one linear layer per convolution. I will get to the usual structure of the network itself.
What are typical sizes of these feature vectors here?
It depends. For classification, which I think is a perfect place to start. Our smallest model gets up to 64, and our largest models get up to 128. Like 64 was fine for me; it was more than enough. For like N-Caltech neuromorphic version, the biggest model got much better results, obviously.
64 numbers.
Yes, this is the length of the output vector.
What precision then? I'm trying to get.
Okay, I'll get to the quantization and the structure of the network in a moment. Okay, like next slide. Sure, because here only two things to mention, which that's the cosmetics. You had a asterisk here because technically we do not put the feature vector only, but we also append each feature vector with the relative position between currently processed events and its neighbor. So for the first time we apply linear layer for ourselves, we just put 0, 0, 0. This is called self loop. And then when we perform the same linear layer for our neighbor, we take its features and the difference in position in 3 dimensions or 2, we can do either works. So let's assume this one is -1x and 0y, and it was at the same time, so 0 as well. Okay. In this way, we also propagate the spatial information of the event, which helps a lot. Another asterisk, which I don't think is necessary, in the first published pointed convolution, there was yet another linear layer in the formula. So after the bitwise, the element-wise maximum operation, we have this one feature vector, and it just fitted the output one to another linear layer. We don't do that for our implementation. It doesn't change much. We could do that for our implementation. I don't have an idea how to do it efficiently, but I figured it may be good to know. Right? Okay, this is just cosmetics of it, so we can skip it. So the typical graph neural networks have pointed convolutions followed by batch norm and ReLU. We obviously usually have multiple of them. Like we work with 5 for classification, and it's more than enough. But for like object detection, you have to scale them all up, obviously. That's fairly easy to note. At the end of the network, the output from the last layer, we flatten it and put to some huge linear layers for like the classification heads, which is also fairly usual. Going back to the quantization that you asked of, before I forget, first of all, batch normalization is fused inside the linear layer by the end of the training, so we don't have to worry about that in the context of hardware at all. ReLU is like trivial, we don't have to worry about that at all as well. And we perform a very simple quantization and requantization scheme, very similar to what we were saying about. So we basically calculate during quantization we're training, we can calculate 0 points and scales. And for requantization after the multiplication, we have to scale the output value and slide it with 0 points, which is fairly simple. I do have bare PyTorch implementation for all of it. I can just give it to you. It's not available, right? The newest version isn't available open source, but I can share it with you, and that's fine if you want. Another type of layer in models like that are the max pool layers, which are fairly easy to understand. We can start with 2-dimensional max pools, which is like a baseline. 2-dimensional max pool works the same way as for convolution layer. So we just scale down the data with maximum representing multiple vertices with 1. Okay. What we do actually our work, I don't think it's like needed in this case, but I will tell you about it anyway. We apply 3-dimensional max pool operation. I will tell you about it because it's one important mechanism where we scale down the graph not only in X and Y dimension, but also in time. So there is a place at our network, our hard implementation, where we have to aggregate the events for some preset small time window, right? And then we pass it along to the next convolution. This way we limit the amount of memory we need, the computation we need, and everything. Also, what is fairly important, we limit the distance between connected edges from 3 to 1, since having at least 3 times 3 pool fuses connected vertices together, so that in the consecutive layers, the maximum distance between connected edges is 1, so we need maximum 18. We have maximum 18 neighbors. Right? Cool. The only thing that happens when we do that, and I think it's fairly important in the context of this accelerator, is when we accumulate events for some time, we lose the order of the events. Right? We had to accumulate them. And so for the next convolution layer, we forget in what order the events were registered. Right? It would be important later. Right now. So what is important to understand, thinking about this graph convolution in the current form, is that in order to perform a convolution for some vertex, we need to have access to the feature vectors of all events that it could be connected to, in the last 3 time steps. In order to perform this graph convolution in hardware efficiently, assuming we can get the events whenever, we don't know because we don't know where it is going to be registered. We need to store a memory of x times y times 3, and in each element keep the feature vector of the event that was there. You understand? Should I write it? You do. So there's a plenty of memory that we need to use, that we need to store in order to compute such a convolution efficiently for any new event that could appear, right? No, because as long as we never lose the order of events, we can do the same thing as we did for graph generation. We can store only x times y memory with feature vectors and store only the most recent feature vector for a particular memory cell, right? So the important thing at the moment is that we can do that as long as we don't lose the order of events, because if we do, we have to store all of them, because then we can overwrite some information that we are going to need for the event that is processed later, but was registered earlier. Yes?
So the feature vectors are constant across time. Like if I have an event happening at the same XY coordinates, but at different times, the feature vector of that is the same.
No, because the new event could have different sets of neighbors, right? So
But then why do you only have to store the most recent one?
Because the new event will be connected only to the most recent one for each particular memory cell, because of the assumption I made at the very beginning that we cannot have multiple neighbors for the same x and y coordinates. Okay. So there could be some other event there, but it doesn't matter because it will never be connected to anything again.
On the input layer, what would the feature vector for an event look like?
Good question. You can do basically anything. We usually do the polarity of the event, and that will work just fine.
But then your feature vector
one with 3 additional ones. So yes, the first convolution have a very small input, and we usually use 16 outputs elements the vector for the first convolution.
Okay, so the first layer you would basically have an MLP that maps like 4 numbers to 16. So it's
yes, this is what we did for event-based vision. However, we did basically similar thing for audio events, and there we used more elements. That we had like a I don't remember, but you can construct some other input values to the first layer. You could input the exact x and y spatial information, or you could input average position of all the neighbors, which was in fact what we did for the audio. So you can just select something and see whether it's trains fine. So going back, if we do all that, we can just use the course for the multiplication, like load the memory and perform multiplication multiple times for each vertex without reloading memory each time, which I think could be interesting and efficient. Last thing, unless you all wanted to end, we can use different methods of like putting the data into the accelerator. Like the software approach, which we use for training, for example, is we aggregate all of the data, we generate the graph, taking into account the order of events, and then we compute the convolution for the entire graph for each layer one by one, which is lame, and we don't know how to do that. The other like border approach would be event by event approach, where we for each incoming event we update the graph, we take this event along, we update, we perform for this event only the first convolution, then the second, and the third, and the fourth, and the fifth, and only then assuming we perform convolutions sequentially, which we will with this accelerator, we would need to wait until we finish all the convolutions before we accept the next events, which I think is not really efficient. It makes little sense. And also we would increase the amount of memory accesses since we would like to, for one graph, update each layer. It defeats the purpose. So I think the first approach would be the best, but I'm open to other ideas. The idea is to use some kind of temporal bins. So let's assume we need 100 milliseconds of data to make a sensible prediction, but we can split the data into, let's say, as an example, 10 temporal bins, 10 milliseconds each, okay? So we aggregate the events for 10 milliseconds, and for this subgraph, we put it to the network, we generate graphs during aggregation, and then entire subset of the graph can be put to the first convolution and the other and the other. And when we finish computing for this subgraph, we can accept the next one. So the next one can be generated at the same time as we compute for the previous one. Okay? It would be perfect if at the same time we would remember the order in which the events came, so we can limit the amount of memory we need to store. We can do it in software that like just timestamp it locally. It was the first, it was the second. All right. For the length of those time windows, we could just set something random, like 128 of the 100 milliseconds. But what I think could be cool, we would choose it based on the how much time does it take for our architecture to process the previous one. So we can start next as soon as the previous one is finished. So we have to evaluate how long does it take. And then based on that, set the size of the type of the subset, which we could do anything we want with it. Because in software during training, we don't do that at all. We process entire graphs, doesn't change anything in the computation itself. Yes.
And the delta TD dynamic is like the amount of time it's going to take to process depends on the activity, right?
Yes, I don't see a reason why it wouldn't be. Because this is something we do only for the computation. It doesn't affect the like the computation itself. It doesn't really matter as long as we remember the order of events.
Can I ask a question from before? When you said that the memory requirement is XY, does that mean XY for each layer of the network?
Exactly, yes. Between each layer, each two consecutive layers, we need a memory like that. Yeah. All right. So the questions are, does it make sense as a project for us? Do we prefer to do just convolutions, which, as we learned yesterday, is used all the time in robotics at the very highest level? Do we want to accelerate the graph generation at all, or do we want to do it at processor? This is something to figure out. Do we want pooling at all? I think the bigger the computation, the better the result will be in terms of acceleration, but we can do pooling. I haven't tried computer vision without pooling yet, so I'm not sure how well it will get for the implementation of it, but I can try during the weekend. Do we want the second layer on the point-net convolution operator? We can do it, we don't have to. And what do we do with the classification heads? Because I did use pooling, so the amount of data to flatten and put to the linear layer was not like crazy. If we don't use pooling, it would get really crazy. So there's a question about the classification heads, how big we want the feature maps, and so on. What I can give you, if you find this interesting at all, is the pure PyTorch implementation for the graph pipeline. You can train anything you want. I have some data sets, homomorphic data sets ready, so we can do that. I also have an open source accelerator for the particular approach we used, with like partly asynchronous, partly synchronous system, but this is more something. Maybe some modules would prove useful, maybe not. But if you are interested, I can show it to you. And also, there's already some idea about implementing it. So if you don't have any questions, there's another person who'd like to share
So just, I have one question before, going back to the memory. So in this case, I think from the parameter side, we're actually pretty good. Like these linear layers don't seem to be very big because they only map from whatever your feature dimension is to whatever your feature dimension of the next layer is, right?
Exactly.
That's what. But the bigger problem would be the amount of activations that you need to store, right? So you would need to. So what is all the data that you need to store for the graph itself? Because so the graph is kind of the thing that you're operating on. Yeah. Right. So you need to store for each x and y coordinate, which in the first layer would correspond to the image size, right? You would need to store the feature vector and
that's it.
the edge.
You don't have to. It depends how. No, you would have to store the edges as well. So.
Okay, and then I assume that as you go to higher layers, maybe your features get longer, but the image dimension kind of shrinks because then you want to do a classification, kind of like in CML.
Yes.
Okay.
And also for like basic NIST classification, 8 bits, it's a lot. 6 bits are fine. 4 bits, makes sense. So we can do a lot with the quantization.
Okay.
But yes, the amount of data that we store is mostly it is mostly feature maps. The amount of data that we store for the weights is like minimal in comparison to the feature maps.
I mean, I'm just like the reason I'm asking this question is that I was thinking, like, from a story perspective, like the coolest thing that could possibly come out of this, in my view, if we go in an image processing direction, is to say, hey, for whatever open GBS camera that we are developing, this could be the post-processing chip. So it's like the whole pipeline. We will not implement it like this necessarily, but just it would be kind of cool if we had a good idea of like. So what would you like? Just to give some example, like what can you do with it? Like image classification or like object classification, basically from an event stream is one of the applications you could do with this, right?
Yes, object detection. Also, there is lots of work with graph neural networks or on more complex tasks like object detection, but only in software. There is no implementation for FPGAs for object detection. Hopefully, in MAV, there will be one, but I'm not sure we are missing some accuracy yet. But well, graph neural networks are increasingly used for event-based vision. So, and I would say maybe anything up to a point, anything you can do with event cameras, you can do with graph neural networks.
I hope at some point we will use these to optimize netlists and circuits and stuff.
No,
That's the future.
Like also, it doesn't have to be events. Like this is one example of the data that can be described as a graph with the graph representation. We could try EEG if you want. We could try basically any data that can be described as the time series or a point cloud in space-time. Like that.
Oh, okay. And Zia, you want to continue here, or?
Yeah, okay. Me really long. Just a rough idea. Peter and I talked about just before the meeting. So, Peter just said we can put the events into temporal bins, so we can parallel between events. But for simplicity, I'm just going to talk about what are the computations we need for us to process a single event. So the processor, I'm assuming, will accept a new event, which will have a x, y coordinate and a temporal stamp t and feature size, which for the event camera is just polarity, just one dimension. So this is basically the computation that we're going to do. So this weight matrix is stationary for all the neighbors, and then this f in and f out is the input feature and output feature of the graph. And the critical issue is how we find all the n neighbors for the incoming new events, and how we pull the new all the neighbor features from the feature map. So
this is a simple demonstration of how feature map would work naively. So all the because it's from events, it's going to be really sparse. So the white dots in the graph is actually where the data are, and the blacks are just empty at 0. So a naive approach would be just store the entire map into SRAM into memory, and then we just address decoding into it and read out all the neighbor events and itself. So this would be really inefficient. So I came up with a simple idea of using address decoding logic inside the software to basically have a address mapping. So whenever a new event enters the processor, it will go through the lot first and pull in constantly where is there stored points is my neighbor stored in the memory. So upon a hit, the processor will output the address to the SRAM in the compute near memory unit, and the SRAM will output the feature vector into the VBM, and the weight matrix will stay in the registry file, which is stationary for all the for single new events. So whenever there's a miss, the software will just loop itself, finding the next possible neighbors. So this basically is the architecture that. So there are some stuff that's because we need to refresh the lots and refresh the memory as well, because whenever a new event comes in, we need to update the lots with. So for example, with the lots is populated with 3 entries right now. So it's x-1, y-1, t-1, and xy t-1. So when the new event comes in, the new event will replace the lots. We'll update the entry in the lot, and then we'll also update the memory stored in the SRAM of the CNN block. So that's basically how I imagine to go about implementing on hardware. Any comments, questions?
You say you're storing a matrix in the register file?
Oh no, it will be all the non-zero elements inside this feature map. So only store the non-zero elements into the feature map, and the address of the single non-linear non-zero element will be inside the lot. So whenever you try to pull a neighbor of the new event, you go through the lot first, and then if you hit them a valid address, and then you send the address to the CNN. If you don't hit that valid address, you just try to find the next neighbor.
What is in the red file?
What is in the red
file?
Oh, red file is storing the weight matrix for a new event, because the weight matrix is the same for all of the neighbors.
I don't think we have a register file that's big enough to store the.
Yeah, we can size it.
So I think just instead of having that in the register file, it would sit in the SRAM of another core. That's how I would see it. Like we have the weight matrices like loaded into a core, and then this is one additional matrix that we need to store somewhere, right? This the graph representation. But I think in my view at least, right, the complete new memory cores, the SRAM, that's exactly where we would put the weight matrix, right, that we apply. No?
So it depends on
how big is the weight matrix, because for convolutional system, typically weights are.
It's not really a convolution because it's just a P4. So if for the first Piotr just said, it will be the coordinates of it, and then the xy and the polarity. So it can be 4 to 8 and 8 to 16. So that's the size of the matrix.
And
it's such a P4 there.
It's getting bigger.
It's getting bigger for each layer.
Like it's always the size of the input vector times the size of the output vector.
Yeah, so maybe
it's getting to 128 and 428.
Yes.
Yes. So it's not really a convolution that you move along the feature map.
Yeah, so it's like let's say a 64 by 64 or something for the linear layer, right? But then so this is the weight matrix, and then this matrix here for the events like the graph, whatever, to keep track of the events that you've seen, that would be output dimension of the layer times size of the feature map. You're saying, okay, let's store where we have events, And then a lookup table for every event where we the features themselves you don't you only store features for events that actually exist. It sounds a bit. I think I get that part. It's just this matrix that stores our activations or whatever we want to call this, like the events that we have seen and so on, right? This is dynamic data. The linear layers, they are static parameters that don't change.
Yes.
We want to store the static parameters in SRAM of the compute near memory cores. This dynamic data, we might also want to store in SRAM if we reuse it for that purpose, but I could also see storing that in this tightly integrated memory that the processor has.
Okay.
Either of these.
Yeah.
It's just I'm saying what we probably cannot do is store the static weight matrix in the register file, like that we don't have a register file for that. Make sense? Or...
Yeah, we can introduce for that because there are some more problems that, so for example, if we're keep receiving new events, right? For example, this data will get 2.0, so t minus 10. If we don't have the data at xy minus 1, x minus 1 minus y minus 1, this data will always stay in the line. So the lot would grow. There's no guarantee how large it will grow. So we also need some refresh mechanism that constantly refresh the memory stored in the SRAM or wherever we want to store the feature map and the lot itself. So that's something yet to be figured out.
But if you're already in multiple places doing some sort of sliding memory thing where you only remember like features of the last event or something, could we do the same here? Like
there is, if you want to do the naive position, just allocate the memory X times Y. You don't have to update anything. You just never access events that are too old. But if you want to do it more efficiently, so keep the data much smaller than X times Y. You have to like look through it and forget those elements which are no longer.
Because you will only know this data is old when there's a new XY. If this data never gets hit, like a cache, right? It will just stay there. Yeah.
But for this lookup table, you would still need to scan through the entire thing, basically.
I'm thinking to put this thing in software, done in the processing.
The other option would be to just store the naive thing that you showed there, this matrix, and because then it's very easy to just scan a very small region around the event that you have, and then just and then check for every one of them. Do I have something? Yes, no. So you would have binary values, and it might be much easier to process.
Yeah, the motivation is the event camera generate sparse data. That's the only reason I came up with this solution. So we can see how things plays out.
Okay, cool.
Right. Because in this way we use the sparsity of data only for computation, but we keep the memory for not maximum size.
Yeah, but I mean, so the memory here is like theoretically yes, but in practice it might not. I'm not sure. Yeah, if your image is like 1,000 by 1,000 pixels, then yeah, it's a million bits. That's
and also I'm not really sure. Like if we just store it in here, right? We also need to search. We also need to read the memory every time we try to find a neighbor. So I don't know how much expensive is that.
Yeah, but it depends how long your lookup table is. Like it might be that scanning linearly through the whole lookup table might actually take longer than scanning a small region in the not spot in the right.
Yeah. And as there's only maximum of 29 edges, we can just alongside with the features store 29 bits of the information where the event where. So this is what we do for our implementation. We just store the ones and zeros where we do have the edges, and we access the memory only for those places where we do have.
Or for each event, you could store a queue that is at most 29 long, or then I think there's many different ways. So, but it's cool. I think it's nice.
Oh yeah, it's cool. I was gonna ask a more general question for these like event processing pipelines. How robust are they to noise, like random events and stuff like that?
Oh, that's interesting question. There was like a recent work on how different methods for event-based processing work with noise. To keeping it short, there is a lot of noise. it doesn't help at all, but we can still keep the accuracy quite high. But obviously, what we would like to do in the perfect case is has a pipeline that between the processing system and the sensor itself has some filtering. There are hardware implementations with absolutely high throughput for filtering. Usually, we would like to do that.
Gotcha. Okay. Yeah, fair enough.
Yeah, there was some work in this report this year about the noise injection for training for different methods, but also the neural networks and all that.
Okay, sounds good.
Very dumb question, like, is this actually good? Like, is this if you compare it to like much dumber methods, like you just accumulate events into frames and then classify them or whatever people have done before they did this? Like, is there some, like, is this like using these graph neural networks like much better than results that people got before? Does it enable you to do stuff that people couldn't do before and so on? Like,
well,
it's a
if you want the state of the accuracy, you just accumulate event data and put it to the visual recurrent network, and you get the best of it always. Like the state of the accuracy are with the transformer, recurrent vision transformers, not with it.
Even like even if you work with event streams, like if you take an event stream,
you accumulate it, you create a representation or the form of graph, you encode it, you put it in the transformer.
Maybe a simpler.
What we get here is first of all the sparse processing of data. We only process the data where it's active. We only process the events which are there. You don't have to scan through the entire representation, which we would do for convolution layer, for example. Also, which is fairly common for software, not yet available for hardware, is voxel graph representations, where instead of creating this graph of a huge size, you first basically you do two-dimensional max pooling before the first layer, before the graph generation. You accumulate multiple events with single vertice, with some kind of data, like the average position or whatever. And then it's get even more efficient and asynchronous processing. You can compute the data. Oh, I did say that in this context, like 1 second, because what we can do, which the convolution can't and the recurrent networks can't as well, we can output the prediction after each subset based on the information from the last 100 milliseconds with no problem. So even though we will output the first prediction after 100 milliseconds, but we can predict the output the next one in the 101 millisecond based on the last 100 milliseconds of data. So it's like we can increase the throughput.
You can reduce like the latency to like classification, sort of.
Yeah, we could do that with recurrent transformers. I think as I think about it now, but yeah. So
yeah,
usually efficient processing taking account the sparsity.
Yeah, I just wanted to ask you, it's a kind of a neat question, but is it worthwhile doing it, right? Like, do we think these methods have a place in the future of event-based vision processing? Is this where people are headed? I don't know, like, are there problems that you can only solve like this? Is it beating some benchmarks, or is it just like cool, but people don't really know yet?
It is a little bit cool, but people don't really know yet. Like graph neural networks are getting increasingly, like, people like to publish about it. There's more and more papers about it in context of vision as well. David Scaramuzza published in Nature.
Yeah,
it's his graph neural networks so that's what happens quite often for moving cameras. That David Scaramuzza does something and then the world tries to mimic that. So I think there are a lot of people who will be better suited to answer this question. I do think that this is something worthwhile, but I have to think that since I put like 2 years of work into that already.
Cool. Yeah, I think this is really nice. I think maybe we should try to think about this. If people who are interested in this, we should all get together. And so what could be the next step for us? It seems to me like all of the operations here should be just, I didn't see anything that we couldn't do in here. I'm not really sure.
Yeah, I think I agree with that. I think seeing like an actual model would be helpful. Like if you say the Jupyter notebook or something.
I can send you in like a second the code. I have like a model in Python to call the layers and everything. I can just send it in a moment. I didn't write the software part of code, so please do not share it. It's my friends. You can share the hardware code anywhere you want. It's mine, I don't care. But for the group here, I'm not sure what I can put it at the Google Drive maybe. I can fork the repository and add you all, but it doesn't. I can create a branch on your repository and push it to the repository along with the Maverik.
It also doesn't have to be all complete, right? In principle, it would even be enough if we see what are the operations that you're doing and then how, like, you know, like if you have like a top level view, or for me at least, it would be.
Yeah, in terms of PyTorch and model view or something.
Yeah, what are the layers, layer sizes, operations, what's the sequence there? So
You want to see it right now? I think I have it, but I expect you would like to eat something.
Right?
Yes, the pipeline is we train it fully with full precision. Then we quantize it and perform a couple of epochs with quantization aware training. And usually we get basically the same results with 8 bits than we do with, oh, come on, with full precision.
we are on Zoom and this is being recorded, so you need to think about what you want to show.
All right, that's fine. I think.
Is that the code you didn't want to share?
That's fine.
Like the top of it is available open source, our previous implementation. So like the stuff that's more like should be secure is not. That is really helpful.
No, that's also, I think, I mean, okay, we don't know what these numbers are, but I think if we knew what the number for, if it says like config.
Oh, so I think a better thing to show you could be this one.
I don't understand why the lights are like columns.
For object classification, we use 3 sizes of models, each with 5 convolutions. Each has first max pool after the first one and the second one after the third one. So the pooling is here and here. We have 16 output layers for the first convolution, which is in there.
But they're on the processor. It takes a while.